So since it's the top of the hour, we will begin with a brief word from our IOC chairs.
Great, thanks, Sam. Welcome, everybody. On behalf of the IPPW International Organizing Committee, welcome to IPPW 2021. My name is Ashley Corzin from NASA's Langley Research Center, and I'm the U.S. co-chair for IPPW. This is the 18th International Planetary Probe Workshop, which was originally planned to be held in Tokyo, Japan. While we are disappointed to be unable to hold IPPW in Tokyo this summer, we're very grateful to the local organizing committee in Japan for all their planning efforts for having to make the difficult decision to hold the workshop virtually again this year. For those new to this community, the International Planetary Probe Workshop is an annual congregation of scientists, engineers, and technologists from around the world working in disciplines supporting planetary probes for exploration. The first IPPW was held in Lisbon, Portugal in 2003, and in the years since, IPPW has alternated between the US and Europe as a nearly annual event. For many of us, it's the best week of the year, and it is truly great to see so many familiar and also many new names joining us for today's first session. Next slide, please. This year's technical program will consist of 6 technical sessions from today through August the 10th. We encourage you to check the IPPW 2021 website for more details on each of these sessions, as well as to register for each of the remaining sessions. Next slide. Part of IPPW every year is the honoring of a scientist, engineer, technologist, or mission planner in our community with the Alvin Seif Memorial Award. The Al Seif Award recognizes outstanding career contributions to the understanding of solar system atmospheres and our planetary atmospheric flight utilizing probes and our entry, descent, and landed systems, as well as the mentorship of the next generation of solar system explorers. Our award recipients will deliver a lecture to IPPW each year, and 2 Al Seif Award lectures will be part of this summer's program. Ms. Michelle Monk, one of the 2020 Dual Award recipients, will give a lecture on Tuesday, July the 20th, and Dr. Athena Kusenis, the 2019 award recipient, will present her lecture on Tuesday, July 27th. Our other dual recipient of the 2020 award, Dr. Ralph Lorenz, will deliver his lecture at IPPW 2022. Next slide.
So good morning, good afternoon, and good evening also from Europe. My name is Robert Buchwald from ESA's European Space Research and Technology Center, and I'm the European co-chair of the IPPW International Organizing Committee. Since its beginning, IPPW always had an important educational side. We do embrace students from all over the world and encourage them to participate, learn, and exchange together with the professionals. I'm particularly happy that we've received also from them abstracts of such a quality that they will be presenting their results as part of the virtual workshop amongst the professionals. Besides this, the Student Organizing Committee has organized the student social event for giving the students a chance to interconnect to each other, and a virtual development session where students can meet professionals and get some guidance and advice on their professional development in a casual atmosphere. For additional information and registration to these events, please go to the website. And for the organization of it, I would like to particularly thank Siddharth and his team for the continuous support also in this year, and would like to take the opportunity to encourage European students to contact Siddharth or myself if you're interested in supporting the Student Organizing Committee in the future. Go to the next slide, please. In parallel to organizing IPPW 2021, the planning for IPPW 2022 has already begun. IPPW 2022 is going to be hosted by Analytical Mechanics Associates and NASA Ames. The local organizing committee is picking up speed with the planning and has allowed me to disclose that, if everything goes as planned, we are going to meet in Monterey in California next year, and finally physically again. I'm really looking forward to that. It has always been a good tradition that the future LOC would also give a presentation on the plans for next IPPW at the closing session. So stay tuned for their preview as last presentation of the last virtual session on August 10th. So before we start, we would like to acknowledge that IPPW is run entirely by volunteers, with countless people serving in committees and devoting their own time to plan and conduct our yearly events. We would especially like to thank Analytical Mechanics Associates for providing our website and announcements, JPL for the virtual meeting support, Richard Otero for the IPPW submission site, the program organizing committee chairs and session conveners for building such an exciting technical program, and lastly, everyone who submitted content for this year's workshop. Back to Ashley.
With all that having been said, Robert and I are honored to declare this year's IPPW open, and we're very much looking forward to an exciting set of virtual sessions, starting with today's sample return to Earth. Program Organizing Committee, we'll hand it back over to you.
And we will hand it over to our session chairs. I believe, Marcus, you're on deck.
Yes, thank you. So hello everyone. My name is Marcus Lobia, and I'm excited to be co-chairing this session today with my colleagues Benoit Pigneur and Raj Venkatapati. We want to welcome you to the first of several IPPW 2021 virtual meetings this summer. This first session is focused on sample return to Earth missions, and will cover technologies, concepts, and projects that have a sample return to Earth element as part of the mission architecture. While much of the focus will be on the entry, descent, and landing aspect of the sample return phase, for many of these missions, there's also challenges in other areas, such as planetary protection requirements and the high reliability design of sample return systems. We will start today's session with a keynote talk from Professor Yuichi Tsuda on Japan's recent Hayabusa 2 sample return mission, followed by an invited talk from Dr. Bobby Braun on the Mars sample return mission, currently in development by NASA and ESA. After these mission-focused talks, we are thrilled to have seven oral presentations, as well as a short poster session in the middle of our session today. In terms of logistics, let me cover a few points really quickly. First, we ask that all attendees not presenting to please keep their microphones muted. Samdata and Jacob Israelevitz are two of our WebEx moderators today, and they will be monitoring the WebEx and muting attendees if needed. So thank you in advance for your cooperation on this to help ensure a smooth session. Next, all presentations today will be run by Tim Bryce, who is another of our moderators. Speakers should unmute themselves at the start of the presentation and should ask for the next chart to be advanced when appropriate. And then finally, for the Q&A periods after each talk and after the poster playback session, we ask that attendees please submit their questions via the chat feature in WebEx. You will hopefully see a small icon in the bottom right corner of your screen. Click on this to expand the chat window where you can type in your questions. My co-chairs and I will plan to read the questions from this for our presenters to answer. And let me emphasize that we please ask you not to unmute to ask questions, as this can make it difficult to control the session when we have a large audience like today. So with that out of the way, let's get started, and I hope you enjoy the next roughly 3.5 hours of great content that we have today. Okay, so for our keynote talk today, it is my pleasure to introduce Professor Yuichi Tsuda from JAXA, the Japan Aerospace Exploration Agency. Professor Tsuda received his PhD degree in aeronautics and astronautics from the University of Tokyo in 2003. After graduation, Professor Tsuda joined the Institute of Space and Astronautical Science, or ISAS, part of JAXA in 2003 as an assistant professor, where he later became an associate professor in 2014 and full professor last year. At JAXA, he has worked in a variety of roles, including deputy lead for the JAXA IKAROS Interplanetary Solar Sail Technology Demonstration Project from 2009 to 2013. He also started as a project engineer on the Hayabusa 2 mission in 2010. 5 years later, he became project manager of the Hayabusa 2 mission and led it to a successful landing late last year. And he will talk much more about this shortly in our session today. In addition to Professor Tsuda's long history at JAXA, he has had the opportunity to come to the U.S. as a visiting scholar in 2008 to 2009 at both the University of Michigan and University of Colorado Boulder. His research interests include astrodynamics, spacecraft systems, and deep space exploration. Professor Tsuda is a recipient of 24 awards and has published over 60 first author papers. Finally, I would like to express our appreciation to Professor Tsuda for attending today, especially considering that this session is starting at 11 p.m. local time in Japan. So with that, I will turn it over to him to talk more about the Hayabusa 2 sample return mission.
Thank you very much for the introduction. Can you hear me? Is that working? Probably yes.
Yes, we can hear you fine. Thank you.
Okay. So first of all, thank you very much for inviting me to this exciting conference. My name is Yuichi Tsuda, and from JAXA, and today I'm going to talk about the achievement of Hayabusa 2. The Hayabusa 2 is a Japanese asteroid sample return mission, which visited an unexplored asteroid Ryugu, and I am leading this mission as the project manager. And the Hayabusa 2 successfully landed twice on Ryugu and created a big artificial crater and deployed as many as 4 mobile robots on the surface of the asteroid. And all in success, Hayabusa 2 returned to Earth last December. So in this talk, I would like to go through the whole round-trip journey of Hayabusa 2 and what we achieved in the Hayabusa 2 mission. So next slide, please. Yes, so this is the mission scenario of Hayabusa 2. The target of this mission is a C-type or carbon-rich asteroid, Ryugu. And it's a 6-year mission launched in December 2014. And after the 3.5 years of the interplanetary cruise, it arrived at Ryugu in June 2018. And then spacecraft stayed in the vicinity of the asteroid for 1.5 years, doing many exciting and challenging attempts, including the deployment of the surface robots on the surface of the asteroid, and also 2 touchdowns, and the 1 kinetic impact mission, which is to create the artificial crater on the surface of the asteroid. And then it departed the Ryugu in November 2019, and then after 1 year of cruise, it returned to Earth on December 6th last year. So next step, please. So okay, now let me briefly explain about the scientific significance of the Hayabusa 2 mission. So could you click once? Yes, and once again. Yes, thank you. So in this picture, you see the solar system from Mercury to Mars. And if we plot small bodies discovered through the ground-based telescope observations, it appears like this. So all dots correspond to the different small bodies. And as of 2021, there are more than 1 million asteroids found. So could you click twice? Yes, thank you. And then the number of discovered asteroids are increasing thanks to the evolving performance of telescope and the technique to detect dark and faint objects. So now you can understand that the solar system is not a sparse world, and it's a very busy space full of small bodies. So therefore, it's important to study about small bodies to fully understand about the formation history of the solar system. And then Ryugu is orbiting around the sun in between Earth and Mars region. So could you click again? Yes, so this is the orbit of Ryugu. So it's an elliptical orbit between Earth and Mars, and its period is about 1.3 years. So it's a bit longer than Earth. So next chart, please. Okay, so so the Ryugu is a special asteroid in a sense that it is estimated to have a rich organic compound and the hydraulic minerals, namely carbon and water. And you know, carbon and water are the 2 essential ingredients of life on Earth. So if you look at the universe through this special asteroid Ryugu, then you can understand not only about Ryugu itself, but also about the history of the solar system and the origin of water and life on Earth. Bringing the sample of Ryugu back to Earth is the most effective way to realize this scientific goal. So next slide, please. So Hayabusa 2 looks like this. So it's a 600-kilogram spacecraft with a 6-meter span tip to tip. So it's a relatively lightweight spacecraft in spite of very large orbital maneuver capability enabled by the ion engine system. As many as 15 scientific instruments are aboard the spacecraft, like cameras and robots, sampling system, kinetic impact system, and so on. So next chart, please. So, okay, so since this is a planetary probe workshop, I guess it would be of interest to you to show the feature of the Hayabusa spacecraft in this way. So Hayabusa 2 carried out as many as 12 daughter probes, most of which were deployed to the surface of Ryugu. And then could you click? And once again. And once again. Thank you. So most of them were deployed to the surface of Ryugu, and the only exception was, of course, the reentry capsule, which returned to Earth. The spacecraft itself was delivered to the surface of Ryugu twice for sample collection. So next chart, please. Okay, so this is the orbital design of Hayabusa 2 from Earth to Ryugu. And the key to realize our round-trip mission is the ion engine system. It's a very high efficiency propulsion system, 10 times more efficient than the ordinary chemical rocket engine. And by making full use of it, Hayabusa 2 could reach Ryugu and then return to Earth despite very compact spacecraft body with a variety of scientific instruments. And then next, please. So Hayabusa 2 arrived at Ryugu on June 27, 2018. Already, it's 2.5 years from now. And the appearance of Ryugu was surprising. It was found to be a top shape with very symmetric appearance. The diameter is approximately 900 meters, and the bulk density measured through the gravity measurement was found to be 1.2 gram per cubic centimeter. And so it's a very porous structure, and it has a retrograde rotation with a period of about 7.6 hours, about 3 times faster than Earth. And the biggest headache for us was that Ryugu was covered with fluoro borders all over the surface, and so we could find nowhere to land. So next chart, please. Yes, so this chart shows the basic asteroid proximity operation strategy of Hayabusa 2. The spacecraft basically hovers 20 kilometers above the asteroid along the asteroid Earth line, and it sometimes moved horizontally, keeping the 20-kilometer altitude to observe the asteroid from different angles, like this chart. And click again, please. Thank you. So when we wanted to do, could you go back one? Yes. So when we wanted to do the higher resolution observation or landing, then it moved along the sub-Earth line. The spacecraft Earth distance at that time was 240 million to 300 million kilometers, which corresponds to 13 to 20 minutes one-way light time. So the spacecraft had to do the guidance and navigation autonomously when it approached below 500 meters. And next chart, please. Okay, so the critical operation we carried out was deploying 3 rovers out of 4 satellites. And the first are the Minerva 2-1A and Minerva 2-1B developed by JAXA. And the one is called Mascot, which was developed by German and French partners. And all these successfully landed to Ryugu and did autonomous mobile activity. And this is the world first successful multiple and mobile activity surface exploration robot on a small body. Next slide, please. Okay, in the meantime, we were struggling to find a way to land a bumpy asteroid. Our original landing accuracy specification was 50 meter, but found that we had to improve to 3-meter landing accuracy to achieve the safe landing. We did many additional survey of the asteroid surface and also many tests and the simulations to improve our landing accuracy. The key to the final solution was here. Could you click once? The target marker, like this movie. So the target marker is a 10 centimeter diameter reflective ball, which works as an artificial navigation landmark. And the spacecraft can detect this as the bright spot by the onboard camera. And we decided to drop the target marker first, like that movie, to know our actual terrain relative guidance capability. And the result was shown in the right bottom figure. Could you click on? Yes. So the point two red line crosses is the aiming point of target marker, and the target marker was actually settled 15 meters off from the target point shown by green square. And next chart, please. Yes. So while dropping this target marker, we did an important autonomous guidance and control testing. We instructed the spacecraft to chase a falling target marker using its autonomous image tracking capability. And the result was shown in the top left movie, and it was so successful. And with this test, we've got a strong confidence to be able to use the target marker for the terrain relative navigation. And originally, the objective of the target marker was to eliminate the terrain relative velocity to realize a pure vertical landing, which was essential for the safe landing. But at this moment, we decided to utilize target marker to control the terrain relative position as well. The strategy what we finally built up was shown in the main figure in this chart. And first, we placed the target marker, as I showed in the earlier slide. And the second, find a safe place near the target marker, and then finally land to the ground using the target marker as the provisional landmark. So next chart, please. Okay, so here's I'm showing the autonomous landing sequence of Hayabusa 2 below 45 meters. It first makes a descent toward drop the target marker, and once the onboard camera successfully finds the target marker, stop at the altitude of about 8.5 meters right above the target marker, and then move horizontally like this to a waypoint right above the landing target point. And then after adjusting its attitude to the final landing orientation, to coming soon, like this, and then it makes a free fall from 8.5 meters. And the final landing phase is instantaneous. When the spacecraft detects landing, the projectile was ejected from the root of the sampling system, and the reflected soil was collected through the sampler horn and then transported to the reentry capsule. And then the spacecraft immediately makes an ascent to escape from the surface. So it's a touch and go procedure. Next chart, please. Yes, so this is the final landing sequence observed by the onboard camera. So you can see the beautiful touch and go sequence successfully completed. And please just imagine that the fact that this was done 300 million kilometers away from Earth autonomously. And the resulting landing error this time was only 1 meter. So next chart, please. And then next thing we did was a novel experiment, which we call the kinetic impact, which is to make an artificial crater. And soon the small probe called impactor will explode. So before that, the spacecraft has to escape to the backside of the asteroid to avoid the explosion debris. Like this. And then the impactor is activated and then make a hole on the surface like this. And next, please. Yes, the process of cratering is something we don't want to miss. But the spacecraft itself cannot observe it because it's escaping. So a very small deployable camera is separated just before the escape is completed, and to observe the impact process staying at the dangerous place, and send the movie data to the mother spacecraft before it is killed by the debris. And next, please. And it was very acrobatic operation, but we succeeded in it. And you can see the crater forming process in the movie in the top, and we could even observe the impact point before and after the impact, and found that 18-meter diameter crater was generated. And the observation of the impact process and the crater terrain are already valuable science, but the most exciting science should be to get the subsurface material exposed by the kinetic impact. So click once, please. Yes, so like this. So we decided to run here to get the subsurface material ejected from the crater and accumulated in the vicinity of the crater. Next chart, please. Yes, the second touchdown was conducted on July 11th, 2019, and it was perfectly successful. And this time it's more beautiful than the first touchdown because the landing accuracy this time was as small as 60 centimeters. Next, please. And this chart shows the summary of the Ryugu proximity operation, showing the comparison of the original plan versus actual history. And we planned to descend 17 times, and actually we did 18 descents. There were actually many schedule changes and rearrangements to adjust to the harsh environment of Ryugu, but the number of descents strongly constrained by the fuel budget was almost as planned, thanks to great effort by the operation team. And we planned to do minimum 1 landing and maximum 3 landings. And in reality, we faced terrible hardships to find a safe place to land. But finally, we could make 2 landings and sample collection from 2 different sites. And we delivered 4 surface robots as planned, and also we succeeded in orbiting 3 objects around the Ryugu to contribute to the gravity science, actually which was not in the original plan. So next chart, please. Okay, so after all these challenging attempts, IPPW departed Ryugu on November 13, 2019, and about 1 year later, it returned to Earth. And the last 2 months required very precise guidance so that the spacecraft should land to a designated landing zone in Lunar Desert, Australia. The terminal guidance required very precise orbital maneuvers, and in our case, we had 5 trajectory correction maneuvers using the chemical reaction control system before the sample return capsule separation, and the 1 additional TCM after the separation to put the spacecraft away from the reentry trajectory. Next chart, please. Okay, so the reentry capsule was separated from the spacecraft 12 hours before the reentry, about 220,000 kilometers away from the Earth. And it flew ballistically toward the atmospheric reentry, and 1 hour after the separation, the spacecraft diverted from the reentry orbit so that it could escape from the Earth's sphere of influence and continue to the extended mission. The sample return capsule, or SRC, has no orbital maneuver capability and just flew ballistically. Its sequence was controlled by the preset onboard timer and accelerometer, and it made an entry above the Australian desert in the midnight. And at the altitude of 10 kilometers, it detached the heat shield and deployed the parachute and started the beacon signal transmission until it landed to the surface. So next chart, please. Okay, so this is the fireball of the IPPW sample return capsule. And you can see beautiful light trail in the sky of the southern hemisphere. So after this, at the altitude of about 10 kilometers, the capsule detached the heat shield and deployed to land softly on ground. So after this is observed from the ground, Cooper Brady City in Australia. So next chart, please. Okay, so this shows the reentry trajectory, and the flight was very precise, and the SRC landed well within the landing zone designated by the Australian authority, which size is about 100 kilometer by 150 kilometer ellipse to cover the 4 sigma landing era ellipse. And on the day of landing, there was a strong west wind in the upper layer atmosphere, which was taken into account in our final EDL flight path analysis. And the resulting landing area from the estimate was below 10 kilometers, which is good enough for the recovery team to retrieve the SRC immediately. And for the recovery operation, we sent 73 staff from Japan to Australia. And, you know, it was really difficult situation because of the worldwide COVID-19 pandemic. And the size of the team was minimized, and we went through all the quarantine process required by the Australian government before starting the field operation. Next chart, please. Okay, so the capsule was immediately found by the ground retrieval team. And we set up an on-site quick look facility where we could extract the gas state sample expected to contain in the sample container in the SRC. And the reason why we did it on site was that we wanted to do it before it was contaminated by Earth's atmosphere. And we successfully retrieved the gas sample originated from Ryugu. We confirmed that it was actually originated from Ryugu because its component was different from the Earth's atmosphere. And then the SRC was transported to Japan and brought into the curation facility located in the JAXA Sagamihara campus within 57 hours from the atmospheric reentry. Our criterion against the contamination was 100 hours time limit from the atmospheric reentry to bring it into the curation facility. So 57 hours is really a satisfactory result for us. Next chart, please. Click again. Thank you. So, after bringing the capsule into the curation facility, we opened it and we confirmed 5.4 grams of Ryugu samples there. So our mission criteria was 0.1 grams, so it's far more samples than expected. And actually, the sample within the sample container consists of 3 chambers, isolate chambers, to store the sample from 3 separate landings. And we actually have 2 landings, and they are stored in a different chamber. So we could analyze it completely separately with this system. And next chart, please. And we also successfully retrieved all the flying parts of the SRC. And you can see the instrument module, structure, and fore and aft heat shield. And there's a flight environment sensors and memory in the SRC. And we could retrieve the flight data of the SRC during the reentry. So we are doing the post-flight analysis using these flight data and the retrieved parts of the SRC now. Next chart, please. Okay, so as I explained earlier, the spacecraft escaped from the reentry corridor after separating the SRC. The spacecraft is completely healthy now, and after separating the reentry capsule, has to continue its flight to head to 2 new asteroids, 2001 CC21 and 1998 KY26, as extended mission. And this extension was proposed to the Japanese government in early 2020, and after seeing the success of the sample return, this new plan was authorized. And this extension is to contribute not only to the new science and technology in the new asteroid, but also to the planetary defense technology and science. Next slide, please. So this is the final slide, and let me. This chart just is showing the what I already talked. So let me conclude my talk with this. Thank you very much for your attention.
Professor Tsuda, thank you again for that great presentation. So we have a few minutes for some questions. I see 2 in the chat window, so I'm going to read those. But if others still have questions, now is the time to put those in. So question number 1 is from Siddharth Krishnamurthy. And so his question is, how did you test these complex maneuvers during the design phase?
In the test, design phase, before launch, you mean? Okay, so first of all, our technology is based on the Hayabusa 1, and we in the first Hayabusa more than 10 years ago, we had many troubles when we do the touchdown, and we learned a lot from that, and we reflect that experience to our design of the Hayabusa 2 mission. And also, besides that, what we did is the simulation and the hardware in the loop verification. And what was more important is that after the launch, we did many operation training using the hardware in the loop simulation with the full operation team many times. And actually, we did about 48 training sessions for landing and descent and landing, and we put the intentionally added many troubles so that the operator could experience the trouble beforehand. And by doing so, actually the result was that the 22 times crash on the asteroid. So by doing that kind of very severe training, then we could finally make a success in the real operation.
That's very impressive. Thank you. So one more question from Raj, one of my co-chairs. Was there any damage anticipated, or did any occur from the ejecta that was seen during and after the touchdown?
Oh, yes. Thank you for a good question. Yes, actually, we observed the degradation in the some optical sensors like camera and the laser rangefinder, which faced to the ground when it landed to the surface, and the lens of those sensors are covered with the foils, and actually the camera, the sensitivity of the camera was reduced by 60% by the first touchdown. But we expected that kind of degradation. So, but with the 60% degradation of this sensitivity, we still could plan to do the second touchdown. And yes, so that's the damage, but there's no hardware damage besides that.
That's great to hear. So I think we have time for one last question here from Heiko Ritter. The mission extension is very significant. Was this reflected already as a requirement in terms of resources during the development phase?
No. So it's not planned before the launch, but actually our in the development phase we are very successful in the controlling the the mass of the spacecraft. And because of that, we could load more than required amount of fuel for cruising. And because of that, after the launch, we know that there are plenty of margin in terms of the cruising capability. So after the launch, we started planning the extended mission. And lucky enough, we succeeded in the nominal mission. So we proposed the mission extension based on that result.
All right, thank you. That was a very exciting mission, and I think lots of us are impressed to see all of the variety of things that happened during it. And so we very much appreciate you talking today about that with us here.
Thank you very much.
Thank you. So I'm going to turn it over to Raj, who will introduce our next speaker.
Thank you, Marcus. Hello, everyone. It's my great honor to introduce the next keynote speaker, Dr. Bobby Braun, actually. Bobby is well known to our IPPW community. He hosted the IPPW 15 in 2018 in Boulder, Colorado, and IPPW 6 in 2008 in Atlanta. He's also the recipient of the ALSEIF Award. Bobby has contributed to the formulation, development, operations of multiple spaceflight missions, and now he is involved with the Mars Sample Return mission for the second or third time, I don't remember, but anyway, with more than 30 years of experience as a space systems engineer, professor, technologist, and organizational leader, he is world-renowned in the authority in EDL. Dr. Braun is a member of the National Academy of Engineering, a fellow of the AAA and AAS, and the author and co-author of over 300 publications. There's one notable thing that people may not know. He worked on the Pathfinder mission while he was doing his PhD thesis, and he got his PhD thesis in 1996, the year Pathfinder was launched. At that time, he held the title as the first ever EDL lead system engineer on a NASA mission, the mission Pathfinder. Bobby is now the Director of Planetary Sciences and responsible for all aspects of planetary missions at JPL. Dr. Braun, also known as Dr. EDL, it's my great pleasure to introduce you and ask you to give us the keynote address. Bobby?
Thank you, Raj. That was quite an introduction. I appreciate it. Can you hear me okay? I just want to make sure.
Yes, we can.
Yeah,
Thank
great. Thank you. And it's great to be with the IPPW community. It's great to see so many friends on the line here today. And I just want to say, Professor Suda, that was a wonderful talk. And on Mars Sample Return, we can only hope to replicate your success. So thank you for that previous presentation. I'm very happy to talk to you today about Mars Sample Return. It's a passion of mine, and it's, of course, a passion of our community for many decades. What excites me the most about Sample Return is that today we can actually say that it's underway as Perseverance traverses across the surface and begins to collect samples later this summer. Can we get the next slide, please? There we go. So Sample Return has been a priority of the planetary science community for 20 to 30 years, and it's been listed as a top priority in each of the last two National Academy decadal surveys. We'll see where it comes out in the present survey, but I expect it to be among the top priorities yet again. The reason scientifically for this is that the record of the first billion years of our solar system's formation and the formation of life on our own planet has been wiped away on the Earth by tectonics and other changes. But that history is there for our understanding on Mars. And so when we're looking at Mars, we're of course learning about Mars's past, but we're also learning about the very interesting past of the Earth, and in particular, the time in which life began to form on the Earth. From a technology perspective, sample return would be the first, Mars sample return would be the first round trip to another planet. And so it also has technology linkages to plans for future human exploration. That said, MSR is an extremely complex undertaking. It's perhaps more complex an undertaking than anything the Science Mission Directorate has attempted before, requiring a set of capabilities that were not demonstrated 20 or even 10 years ago. And in my view, it's feasible today, frankly, because of the significant investment that NASA and ESA and others have made in Mars exploration. If you look out over the past decade or two, our world has spent $10+ billion preparing people and technologies to accomplish a mission as challenging as sample return. And that buoys me and gives me confidence that we can get it done. Now, in recognition of this complexity and the size and the engineering advances required, NASA and ESA started early on sample return, and they organized a multi-year formulation effort and utilized significant independent review during that time frame. This is not something traditionally that NASA has done before, bringing in multiple independent review boards during pre-phase A. And most of what I'm going to be talking to you about today is similar to the work that was presented to those boards and the findings from those boards. I would say is that as a result of those efforts, we understand the challenge much better than we would have otherwise. We don't have solutions to all the challenges, but we know where most of the challenges are today. The team is continuing to ramp up across the US and across Europe, but many challenges remain. And over the next few years, what's going to happen is that as Perseverance traverses the Mars surface and begins to scientifically select and seal in sample tubes, samples that will ultimately come back to Earth, the Mars sample return team will design, develop, and assemble the next couple of missions in this generational scientific quest. The architecture that we have includes multiple launches of a sample retrieval lander and an Earth return orbiter, and those launches can happen independent of each other in either the 26 or the 28 timeframe. Next slide, please. So this is a depiction of the entire sample return campaign. What you can see here is that to complete the campaign, we've broken it up into 4, and it could eventually be more, but 4 implementable steps. The first step is the one that's underway. Perseverance on the surface of Mars, selecting and caching samples. All the way on the right, we have the sample return handling facility and the scientific curation and allocation of the samples when they come back to Earth. And in the middle, we have a couple of flight systems, a sample retrieval lander system and an Earth return orbiter system, which combined with their payloads and their launch vehicles are the flight systems in development that will launch in the 26-28 timeframe and kind of carry the baton, if you will, from Perseverance on the surface today to the sample receiving and handling facility that will be constructed over time. When we talk about the Mars sample return program, we're talking about the missions in the middle of this slide that are in development today. But when we talk about the campaign, we're talking about the end-to-end campaign, including Perseverance and the return sample handling project required to get the samples and bring them all the way back, curate, and do science allocation. And this campaign is being implemented through a series of launches and one ground element jointly by NASA and ESA. Next slide. Oh, sorry, it's an animate. There you go. So the architecture that we showed at the mission concept review, which was about 8 months ago now, is shown here. And you can see the 3 launches and the ground element listed on the x-axis here. The first launch, of course, Perseverance has successfully landed, and Perseverance is doing its surface operations. The next two launches, an Earth Return Orbiter, which would be launched on a European vehicle, and the Sample Retrieval Lander mission, which would be launched on either one or two U.S. launch vehicles. And those launches can happen in 26 or in 26 and 28 or in 28 and 28. There are even some, with some additional components, ways to extend those launches further, but we would very much like to do those launches in 26 or 28. And you can see the way the architecture rolls out here. The Earth Return Orbiter launch takes a large orbiter that I'll talk about in a little bit more called the Earth Return Orbiter on a transit to Mars. It inserts into Mars orbit and spirals down from where it can observe the surface operations and potentially contribute as a telecom asset to those surface operations. The Sample Retrieval Lander or landers are launched independently and sent to Mars. They perform entry, descent, and landing, and they land with the type of technology, maybe not the same architecture, but the type of technology that Perseverance demonstrated with a couple of additions that I'll talk about in a moment. They carry to the surface, among other payloads, the Mars Ascent Vehicle, and the Mars Ascent Vehicle would lift the samples once collected into Mars orbit, where rendezvous with the Earth Return Orbiter would occur. The Earth Return Orbiter is sized for a round trip, and it comes back to the Earth. And as it approaches the Earth, it releases the Earth Entry Vehicle and then does a deflection maneuver. And the Earth Entry Vehicle comes down and is recovered in the U.S., where the samples are recovered and taken to the receive facility. Next slide, please. So Perseverance, I'd be remiss. I know there'll be several talks on Perseverance in this conference, in this workshop. Al Chen and the team around the country that participated in Perseverance, EDL, they're all heroes. In my view, they did a fantastic job. And Perseverance, the surface operations checkout has proceeded without a hitch. The mission is very much on track, and we should be collecting samples later this summer. It's been an amazing mission so far. I can also attest to the science treasure trove that is at this landing site, Jezero Crater. The scientific community is very excited about what they see already, and so there is going to be a wealth of samples that are for possible return coming out of the Perseverance mission. Next slide. Now, one of the things that we've done in sizing the architecture is to take a look at what Perseverance is likely to do and where it's likely to go. We landed in the upper right of this image in Jezero Crater. And what's shown here is not the actual traverse of Perseverance. This slide was actually made prior to the landing. But what's shown here is a reference traverse that Perseverance may take over the surface as it explores Mars. And superimposed on top of that reference path are areas where we can land the Sample Retrieval Lander and areas where we can conduct surface operations with our Fetch rover that I'll be talking about in just a moment. And what you can see here indicated in the numbers, if you zoom in a little bit, you can see that there are dozens of places where the Sample Retrieval Lander can touch down. And that's important because Perseverance will certainly have acquired samples and will have cached them on the surface well before we launch the Sample Retrieval Lander. So unlike previous Mars missions, we're going to know precisely where we want to land. And we factor that in to the entry, descent, and landing approach so that we can land within a football field of that designated site and reduce the requirements on the Sample Fetch rover for traverse operations. Of course, if Perseverance is still alive, and when we get to Mars, Perseverance will be younger than Curiosity is today, and Curiosity is doing very well, we could actually have two means of delivering samples from Mars, 2 rovers to deliver samples from Mars to the sample retrieval lander. But that's, that's important for us going forward. Next slide. The samples themselves, we're going to collect through Mars 2020, through the Perseverance system, we're going to collect a broad swath of samples that tell us a great deal about the history, the potential for habitability, and even the potential for life on Mars. This is a slide that I borrowed from a presentation Ken Farley gave a few years ago. In addition to the different types of rocks that we will be returning from different geological units over different time periods, there are also blanks that we've brought along with us from Earth that will be returned, and those blanks are there for contamination control purposes and things like that. Next slide, please. Oh, sorry. Go back one, please. I should have mentioned that our plan is to collect and potentially cache something on the order of 10 or 20 samples within Jezero before Perseverance is designated to potentially leave Jezero. Of course, that depends on what we find in Jezero still. But there is a plan potentially for Perseverance to leave Jezero, gather samples from other regions around the Jezero crater, and then return to Jezero or another such site where the samples from both within and external to Jezero could be placed on the sample retrieval lander. Next slide. So we have a number of flight systems that are going to make this possible, and I'm going to talk more about these on the coming slides. But we have the sample retrieval lander, the sample fetch rover on the left. You can see the Mars ascent vehicle lifting off from the sample retrieval lander, the Earth return orbiter shown, and then the Earth entry vehicle. Next slide. So the sample retrieval lander, as designed and presented at our mission concept review, is shown here. It's a somewhat of a heritage cruise and entry system approach. It's a little bit bigger than Perseverance, about 4.7 meters in diameter. It would execute a guided entry, much like Perseverance did, and deploy a supersonic parachute. The main difference from an EDL perspective relative to Perseverance is that it will be carrying enough fuel to execute up to a 4-kilometer divert to take out the errors in the roughly 8-kilometer major axis error that's observed once we get off the parachute. Because of the mass of the payloads that we're taking to the surface, the Mars ascent vehicle, the sample fetch rover, and all of their accommodations, we're looking into a powered propulsive lander. So more like Viking, Insight, Phoenix that we've done before than the Sky Crane itself. Next slide, please. This shows the divert maneuver, and so we would be flying once again with terrain relative navigation, but this time, instead of just finding one of many safe zones for the system to come down in, as we did in Perseverance, we would designate a landing site close to the cache, and we would land probably within a football field of the cache by accommodating a few hundred kilograms of propellant to execute this propulsive divert. Next slide. In terms of the payloads itself, I'm going to focus on I'll just talk about the Mars ascent vehicle for a moment. It's a 2-stage solid rocket design. It's being developed at the Marshall Space Flight Center. It's about a 400 kilogram allocation mass system. The first stage is guided, the second stage is unguided, and it will be the system that takes the orbiting sample, our sample tubes, once they're contained. You can see that just below. They're placed in the nose of the launch vehicle, and then that is what's sent into Mars orbit. The samples are, of course, acquired by the sample fetch rover, which is coming from ESA. It's a 230 kilogram system, about the size of ExoMars or Spirit or Opportunity. It's a solar-powered system. And on the sample retrieval lander, there will also be a sample transfer arm assembly that's being also developed at ESA. And that sample transfer arm will be used to collect samples from either the sample fetch rover or from Perseverance. Next slide. The second mission, the Earth Return Orbiter, and its payload, which will probably launch first, is truly a biprop system, and it will be the largest orbiter ever sent to Mars. You can click a couple times, please. It's biprop because it has a Earth departure stage that is a chem system to leave the Earth, but then it's got electric propulsion to insert into Mars orbit and to spiral down to the right rendezvous with the Mars Ascent Vehicle, spiral up out of Mars orbit and return to Earth. And its only payload is the CCRS, which is being developed largely by the Goddard Space Flight Center in conjunction with Langley, Ames, and JPL. And this is the large structure system that will, upon rendezvous, will grab the orbiting sample, orient it appropriately, contain it once again in a second set of seals, place it inside the Earth entry vehicle, and then return that system to just the right conditions for Earth entry vehicle release when we come back to the Earth. Next slide, please. The Earth entry system is a remarkable system. It's a greater than about 1 meter, 45-degree sphericone. It has passive aerodynamic stability throughout the hypersonic, supersonic, transonic, and subsonic domains. So it is not flying with a parachute. It's a single-stage entry system from the top of the atmosphere to the surface, and it's designed to take ground impact with its crushable energy absorber and the rest of its structure to limit the loads on the rocks themselves to something like 1,100 Gs from a science perspective, and from a containment perspective, it can take as many as 3,000 Gs. Once again, we'll be landing in the soft mud of the UTTR, of the Utah Test and Training Range landing site. Relative to past entry systems that NASA has done, Stardust and Genesis, it will be coming in on a much steeper entry to reduce the footprint significantly on the surface, and it'll have a longer exo-atmospheric flight time, largely to make sure that the Earth Return Orbiter has enough time to do its divert properly because of back planetary protection. I mentioned the fact that it has no parachute, and it's designed largely from a containment assurance perspective. In fact, these samples will be sealed on the order, will be sealed 3 times once inside this system by the time they come down in Utah. Next slide, please. The Earth Entry Vehicle, as you know from past discussions at IPPW, has a long legacy. It was, I believe, originally developed in the mid to late 90s at NASA Langley. It's had a number of improvements made over the last few decades. The folks at Langley and at Ames that are involved in the heat shield have frankly done a great job on this system. There's been a lot of testing of this design already, and we're very confident in its performance. Next slide. So in summary, with the launch of Perseverance, the MSR campaign is underway. In my view, it is among the most important planetary science undertakings in our generation. We have a great team, a full partnership with ESA. We've got 5 NASA centers and NASA headquarters involved in this activity. And we've developed a broad set of options going forward. We're presently in phase A, and you would expect a team with a complex undertaking like this in phase A to be looking at a broad range of options, and we're doing that. All of our options involve launches in either the 26 or the 28 timeframe of both ERO and the sample return lander, and those trades are ongoing. We have reached agreement with the Mars 2020 team about the sample caching strategy. We have an MOU that documents that. And so the idea of these green zones and landing near the samples, that is baselined into our system at this point. The focus of the team today is to close our phase A trades to get a better handle on cost and schedule as we head into additional reviews. And we're working a procurement strategy to bring in a number of industrial partners across this system, both in the US and in Europe. In my view, now is the time to leverage all the investments that we've done at Mars, to leverage the fact that we have perseverance on the surface, collecting samples, and to actually accomplish MSR, this great science quest. One last slide. Next slide, please. I didn't want to leave this topic without mentioning a great talk that was given at IPPW 6 by Mark Adler on this topic. And since that time, it's been called the Adler paradox, and that's the question of when we're going to do sample return. It is a complex undertaking, and in that talk back in 2008, Mark posited that we would have to break it up into a number of missions, 3, maybe even 4 launches. You know, he was right. He posited that we were going to have to push our technologies, bigger parachutes, invest in Mars ascent vehicles, look at back planetary protection and the technologies required there. And frankly, he was right about that. And if you go back to that talk, you'll find a number of areas where he was right. Now, his conclusion of the talk, I disagree with. I disagreed with at the time, and I disagree with still. And what you can see here is the planned date for sample return as a function of today's date. And this is all focused on the sample retrieval lander, because in all concepts, there's multiple launches. And, you know, it's not a great history here. By the way, when the line of multiple of disjointed lines touches the single line, that means we've made it. And you can see that we've gotten close a couple of times historically, only to have setbacks. And what has to happen now, you can see that we're up there with the launch in 2028 of the sample retrieval lander. What has to happen now is we have to conclude our implementation plans. We have to converge our design and stick to cost and schedule. It's something we can do. It's something we know how to do. We just have to get it done. And with that, next slide, I'll see if there are any questions.
Thank you, Bobby. There are 5 questions online, and I will read them in the order in which we received. So first is from Robert Bookwald. Landing so close to the cache, can you elaborate a bit on the risk for the cache when dust and debris is being kicked up by the thruster plume?
Yeah, so we're going to make sure that we land far enough away from the cache that we do not kick up dust and debris, significant dust and debris on the cache itself. We can land, if we land a football field away, and if we orient our descent thrusters in the right way, we can influence that greatly.
Great. The next question is from Marcus Lobia. Dr. Braun, when is it planned to collect the first sample using Perseverance?
Well, I'm hopeful that it'll be in July. It could be in August, but it'll certainly be in the summer.
Great.
And teams made great progress there, and it's really a matter of converging on what the right target is for that first sample, and then just getting it done.
Wonderful. Good luck with that. The next question is from Ralph Lawrence. The InSight experience shows Mars cannot be relied upon to clean dust off of solar arrays, as happened with Spirit and Opportunity. Will the sample return lander be resilient to 0.3% per sol dust accumulation?
That's a great question. Thanks, Ralph. So my answer is yes. There are a number of things that we're doing to make sure of that. One is, frankly, by landing the sample retrieval lander as close to the cache as makes sense, we minimize the number of days that the sample retrieval lander has to operate, right? This is not a mission of exploration. This is that could be unbounded. like Curiosities, for example. This is a mission where we know where the samples will be before we launch. We have to land and gather them as quickly as possible. And so we can, of course, we can double or triple the time that we think it takes us to gather those samples and size the solar arrays for that level of dust accumulation. We can also, although our baseline is not this at the moment, we could also look at an MMRTG for the lander. To me, that feels a little bit like overkill, but that's a possibility as well.
The next question is also from Ralph. It is tempting to think the ascent vehicle is a simple solid rocket, but probably isn't that simple given the atmosphere and the large thermal excursions on the surface. What do you see as the biggest challenge?
Yeah, I wouldn't call it simple. First of all, it's a two-stage system. One stage is guided, one stage is unguided. The unguided stage is spinning. And so to us, the most significant challenge there is really the transition from the guided, unspinning stage to the spinning, unguided stage. And that's something, frankly, that we can test here on the Earth, and we have that in our baseline at the moment. But we're definitely not taking the ascent vehicle for granted. It's something that, from a technology perspective, Marshall, JPL, and folks in industry have been working on for a number of years, and it's definitely a focus of our attention going forward.
The last question on the chat from Samuel Albert. What drove the design of the propulsive-powered lander as opposed to Skycrane?
Yeah, so largely it's the size, volume, and mass of the payloads themselves that we're taking to the surface. So we invented the Skycrane because we couldn't land Curiosity and also Perseverance with airbags. And much in the same way, the powered propulsive lander has been demonstrated to be a more efficient, from a mass and volume perspective, lander than the Skycrane itself. And we have launch vehicles with a particular shroud diameter that we have to fit our aeroshels within, and so that's a constraint on the overall size of the system. And so when you take all these constraints together, the launch vehicle constraints plus our payload, the powered propulsive lander is really the right way to go for this concept. We've looked at it multiple times now, and we come to that same answer.
Thank you, Bobby. I have one question.
Sure.
And, you have mentioned that MSR is an engineering mission, not scientific, in the sense that it doesn't have any science instrument. But given the fact that there will be some exciting things happen, is there any possibility for the ground assets we have at Mars to do some extended science? Is there even a remote possibility or not?
Okay, so that's a great question, Raj, and thank you. I may have given the wrong impression. So first of all, MSR is a science mission. It is, in my view, one of the most important science missions or campaigns for our community in the coming decade. But you're correct, we're not an in situ science mission. We're not a remote sensing science mission. So we're not developing instruments and taking them to the surface. And the science return has to wait for the samples to come back to Earth, which for the Mars science community is a difficult thing because we're asking them to wait for almost a decade for that return based on the investment. So what we're doing in the Mars exploration program, external to MSR, which was not a portion of my talk here today, we have, of course, we're operating the existing missions, orbiters and landers, but we're also looking at what we can do in parallel to MSR through the budget of the Mars exploration program, and trying to determine if there are perhaps some small sat science missions or other missions like that that'll fit within the President's budget request to continue the scientific exploration of Mars. The Mars Ice Mapper is one such proposal. It's a whole different mission being led by at NASA by the Goddard Space Flight Center. It also involves the Japanese and the Canadians in a significant way. And it's a space-based radar that will be orbiting Mars looking for shallow subsurface ice, just as one example.
Thank you. I just want to close this by saying we are living in an amazing period of scientific exploration and discoveries, especially with Hayabusa 2 success that we just heard on the Ear Talk, and also next year or year or so later, the OSIRIS-REx return and Mars sample return in a decade. This is going to be exciting for the next generation of scientists and for the engineering community as well to learn from all of these things. It's amazing time, really.
And it really is.
Yeah.
It's an honor to be a part of it. To be honest.
It is, and I personally and the community, IPPW community, thank you for your support all these years and years to come. Really.
Yeah. Thank you. It's great to be here. Take care.
Yeah, thank you. And I will turn this over to Marcus. Marcus?
Yes, thank you again to our invited speakers today. Those were some great presentations, and I think that really set the stage for the sample return session here. So next up, we're going to transition to our oral talks. And just, I should have mentioned this at the beginning, but we do have the schedule on the website, so you're welcome to look at that. We will have 3 oral talks here before our break at the end of the hour. And during the break, we'll have the poster playback and poster Q&A session, and then followed by 4 more talks to conclude today's session. Okay, so let me introduce our next speaker. Ricardo Bunt is an aerospace engineer with experience in the field of atmospheric flight. After graduating from the Politecnico of Milan and the Delft University of Technology, he joined Demos Space in 2019 and is currently working on multiple projects and studies in the field of atmospheric entry emission analysis for reentry vehicles and launcher stage recovery. Ricardo is also a graduate of the International Space University. In Hearted, he is part of Demos' mission analysis team in support of Thales Alenia Space, prime contractor for the Hearted mission, our Hearted study. So I will turn it over to Ricardo.
Thank you very much, and thank you for the introduction. Good morning and good afternoon, everyone. Can you hear me properly?
Yes, we can hear you.
Okay, yeah, thank you. Okay, it is great to be here virtually at IPPW. Today, I will present the results of a feasibility study of a high-speed entry technological demonstrator, or HARTED. Our team at Demos performed the analysis I will show in collaboration with Thales Alenia Space, that is the prime contractor of the study that has been funded by ESA. Next slide, please. Okay. Today's presentation will provide the motivations and objectives behind the study, and with the presentation of the high-speed entry problem we are trying to tackle. Phases 0 and phases A of the study have been performed with the mission architecture concept proposed and trajectory analysis. And in phase A, a vehicle configuration has been defined with the reference scenarios and alternatives. Next slide, please. So what is the motivation behind the HARTED study? Well, the worldwide experience, as we've just seen, in high-speed re-entry is available to US, Japan, and Russia, whereas for the European background, it does not exceed the typical conditions of a low Earth orbit re-entry of about 8 kilometers per second. For this reason, a hypervelocity Earth re-entry technological demonstrator, or HARTED, this kind of mission will be useful to prove the technology that will enable future European sample return missions. So as I was saying, the study is divided into 2 phases, phase 0 and phase A. In phase 0, we have defined what conditions characterize our re-entry scenario and evaluated a system conceptual design based on different mission architecture concepts. To conclude phase 0, with the help of Thales Alenia, we performed a trade-off activity based on the different architectures identified and selecting a baseline mission. In phase A, we've been looking into this baseline mission and understanding the technical and programmatic feasibility of this concept. Next slide, please. So what is the high-speed entry problem we had to focus on for Hearted? Well, it is we had to understand what kind of conditions we would have to replicate to simulate sample return type of re-entry, so from an interplanetary trajectory. And these conditions have been identified in terms of heat flux and heat load for a re-entry. And we wanted to maximize these conditions without having to provide too much energy to our trajectory, so making the mission design complex. The three key parameters we have been focusing on are the entry velocity, entry flight path angle, and the ballistic coefficient. The first two depend on the orbital strategy and maneuvers we decide to perform, whereas the ballistic coefficient depends on the capsule shape, geometry, size, and mass. So we wanted to identify this sweet spot of entry conditions that would provide us with these entry conditions in line with an interplanetary mission. Next slide, please. Three different candidate mission scenarios have been investigated. The Orion piggyback and the GTO piggyback both rely on flying as a piggyback on a mission. So the needs of the trajectory and the entry would not be only tuned to Hearted's needs, but would have to, of course, meet the requirements of the primary payload, Orion in one case, and the GTO satellite, for example, on the second case. The third candidate mission scenario we have been looking at is to have a dedicated launch for the Hearted mission, so where we could tune our mission design to completely meet Hearted's needs. Next slide. We have been looking into detail in each and every one of these three scenarios, understanding that the technical feasibility of the three. For the Orion piggyback mission, we have found a possible solution of performing a delta V maneuver 3 days before the entry interface point, so during the return leg of Orion from the Moon towards Earth. Performing the maneuver 3 days before allows us to maximize the landing site accessibility on Earth. Of course, we want to detach from the primary mission of Orion and perform a re-entry in a point that suits our mission. The high conditions of the re-entry that we want to achieve would be provided by the translunar orbit that Orion would be flying. So we do not need to accelerate the vehicle in the final phases before re-entry. What we see here is that providing up to 200 meters per second of delta V would allow us to reach a wide range of possible landing sites across the globe, with the identification of offshore Panama landing as a possible solution. Next slide. Regarding the GTO piggyback option, two different concepts have been explored. One with the 2 maneuvers performed, one at apogee of the GTO orbit, and one just before re-entry to give a final kick to our capsule to increase at the end, just before entry, the entry velocity. This concept relies on low amounts of delta V needed, below 200 meters per second, and of course we cannot define a wide range of possible landing sites, as they're mainly limited by the GTO orbit. and by the low delta V we're using. So we would have to wait multiple orbits before achieving, let's say, a whole region of possible solutions along the equator. Whereas if we want to look at the possible landing sites that are above or below the equator, we decided also to consider one maneuver with high energy, so with the delta V provided of in the order of 3 kilometers per second. And in this case, we open up all different latitudes to a possible landing site. Next slide, please. Okay, the dedicated launch scenario. What we have done is to consider a wide range of launches and to select the launches that would provide us with the conditions that we need for entry. So that gives us sufficient energy to accelerate the vehicle to the high velocities we need. These 3 launches identified are the Launcher 1, the Vega, and the Spectrum. Next slide, please. In order to establish what launcher, what candidate solution would be the best one from a programmatic and technical point of view, Thales Alenia performed a trade-off activity with the result of seeing that the dedicated launcher was the candidate solution, the candidate that won the trade-off activity, with a particular focus on the D2 scenario. This is a Kourou launch and the Pacific Ocean recovery. The launch performed on a Vega launcher. Between phase 0 and phase A, also an additional scenario was added to consider also a land landing to Woomera, and this is scenario D6, with a Kourou launch to Woomera landing, also performed by Vega. Next slide, please. Once we have identified that our candidate mission scenario would be a dedicated launcher, we can start defining the baseline configuration for the vehicle. The hearted spacecraft would be composed of Earth re-entry capsule, purple, and an orbital module. The orbital module would have within it is mainly composed of a kick stage that would be used to accelerate the vehicle prior to re-entry. On board the hearted on board the Earth re-entry capsule, we would have all a different set of instrumentations that provide us measurements to meet the objectives, the scientific objectives of the study, especially in terms of understanding the entry environment, temperatures on the heat shield, and after recovery, of course, evaluating the state of the TPS. Next slide, please. The reference mission has been identified for the hearted study at the end of phase A, and this, as I was saying, is a mission from Kourou to Woomera. This allows us to have a landing at the Woomera test range, where we can easily recover our vehicle, or the entry vehicle, to be able to analyze the heat shield. Whereas an ocean landing would make recovery more complex, and of course, if there could be degradation due to the salt of the water in the water landing. This reference mission is performed with the Vega, with launch from Kourou, and we see here different trajectories as different options have been considered depending on the launch heading. Regarding the landing site at Woomera, we were constrained by the heading that re-entry missions have to target the test range with, and we were able, with a series of maneuvers, to meet the heading requirement for the test range. The re-entry conditions are in line with what we wanted to achieve from a sample return mission, so heat flux is above 13 megawatts per square meter, and peak heat loads above 150 megajoule per square meter. Moving on to the next slide, please. We see the backup or alternative mission, that is the Kourou to the Pacific Ocean scenario. In this case, we would be recovering off the coasts of Peru. So it is, of course, a backup solution. Without limitations in terms of entry heading, we can achieve even higher entry conditions in terms of peak heat flux and heat load. Next slide. This final slide concludes my presentation with a few key points. Above all, different missions architecture concepts have been evaluated, from Orion and GTO launch piggybacks to a dedicated launcher for the mission. A trade-off activity has been identified, has been performed, and a best mission architecture solution for Hearted has been identified. The vehicle for Hearted has been proposed in terms of spacecraft, so with an orbital module and a re-entry capsule. And finally, a reference and a backup mission scenario with the use of Vega have been proposed with the entry conditions that are representative of the interplanetary return mission we want to simulate. So from this point, the way forward is the consolidation of the safety requirements for associated to the Woomera landing site, consolidation of the mission scenario involving the launch provider to either confirm the baseline trajectory we have defined or explore different alternative solutions. The kick stage performance has still to be evaluated and confirmed, and these are all points that will be carried on in phases B and C with the detailed mission design. This concludes my presentation, and I'm open to questions.
Thank you, Ricardo, for that great presentation. So we have about 1 minute for questions. Looking at the chat, I do not see any in there. So I just want to encourage folks to, again, if you have any questions for our presenters, please put them in the chat so that we can ask them. So with that, I guess I'll ask one question based on just, looking at your presentation. And you mentioned this is really to test the hypervelocity conditions for European entry systems. Is there kind of one area specifically, or maybe a few areas in particular, that you see as technology challenges to address here? For example, like the thermal protection system, or structural design, or landing accuracy, or things like that?
Yeah, it would be probably the TPS design, as it would exceed what has been tested in Europe, but that's exactly what Hearted expects to do. So to propose a TPS solution and evaluate if it works.
Okay, great. Thank you. So I think we're out of time, so we're going to move on to the next presentation.
Thank you very much.
Thank you, Ricardo. And just, I should have mentioned this, I actually gave a Ricardo warning as well, but for our presenters, I will probably send you a private chat message about 3 minutes before the end of your slot, just as a reminder to wrap up and, if possible, leave a minute or two for questions and answers. Okay. Okay, so our next talk will be given by Jacob Needles. Jacob is a systems engineer with NIRIM Corporation in the Entry Systems and Vehicle Development Branch at NASA Ames Research Center. He holds a BS in Mechanical Engineering from the University of California, Davis, and a Master's in Aeronautics and Astronautics from Stanford University. So Jacob, why don't you go ahead?
Great, thank you, Marcus. So hello, everyone. Thank you for attending today. I'm going to be presenting today on work conducted regarding subsonic tumbling behavior observed in 6th degree of freedom simulation for the Mars Sample Return Earth Entry Vehicle. So this work was conducted with Peter Gage of NIRIM and Jeffrey Hill.
Jacob, I think we lost your audio.
Yeah, I just got a it looks.
You might try disabling your video if you're having connectivity issues.
Okay, is that, can you hear me now?
Yes, can hear you.
Okay. Sorry about that. Yeah, just, it lost for a second. Yes, that's a good point. Let me hop off the VPN as well. All right. Okay, is that connecting better?
Yes, please continue.
Okay, thanks. Yeah, we can go ahead and move to the next slide. Sorry about that. So today's talk has two components. The first is a root cause analysis of tumbling observed in simulation, and the second is application of an analytic stability criterion to characterize design sensitivities. So we can go ahead and move on to the next slide now. So it's been well characterized that blunt body entry vehicles are subject to limit cycle oscillations in total angle of attack, and that under certain conditions, the amplitude of these oscillations can diverge, leading to tumbling, which generally occurs subsonically. Mars Simple Return has baselined a fully passive entry vehicle concepts, and therefore subsonic tumbling is a primary concern from the standpoint of containment assurance, since no drogue chute will be used to stabilize the vehicle subsonically. So far, 6 degree of freedom simulations using the Post2 software have indicated an unacceptable degree of tumbling for a 60-degree sphere cone geometry early in the program design cycle, which has subsequently motivated the MSR program to consider steeper cone angles. And the cone angle system level risk trade has therefore motivated a root cause analysis of the tumbling behavior observed in simulation. We can go move to that next slide, please. So I'd like to start by acknowledging the EUV flight mechanics team, particularly Ben Tackett at NASA Langley, who performed the Monte Carlo simulations using the Post2 software and provided the data sets used in this analysis. Monte Carlo simulations employed 40 dispersed inputs to model uncertainties in state, mass, and aerodynamic properties. Aerodynamic uncertainties are handled using both adder and multiplier terms consistent with past program error databases. So at left here is a table provided by Ben, which shows a subset of inputs for tumbling states. The green to red shading indicates the magnitude of the applied uncertainty. We observe a strong dependence on radial center of gravity offset, but also on CMQ and CN alpha in predicting tumbling cases. Subsequent processing of input data noted that no single parameter fully explained the observed tumbling. We then consider the Monte Carlo outputs, and it was observed that without exception, all tumbling cases developed high roll rates, much higher than those anticipated along the nominal trajectory. So at right here, we see a plot of roll rate for the 50-degree configuration plotted against geodetic altitude. And from a release roll rate on the order of 12 degrees per second, we see a rapid spin up during the dynamic pressure pulse. And we focus on the roll rate at the end of the pressure pulse. And note for the 50-degree configuration, those roll rates are on the order of 200 degrees per second. If we do a similar processing for the 60-degree sphere cone geometry, we see roll rates on the order of about 90 to 100 degrees per second, so roughly half. We can move to the next slide, please. So the question then is what causes this roll behavior? And we know that it's not explained by spin eject or nominal roll during entry. So the conclusion is that an additional physical phenomenon is at play. Slender body military reentry vehicles have been known to exhibit roll anomalies due to configurational asymmetries in mass and aerodynamic properties. So we hypothesize this is the case for EEV. So at left, we see a plot with roll rate plotted on the z-axis and the cross product between hypersonic moment coefficient adders and the radial center of gravity offset, the magnitude of which characterize a persistent roll torque. And we note that there's a direct correlation between the magnitude of this adder and the degree of roll-up observed during entry. So that is, in cases where the interaction between these adders is large, we see a large roll-up. And at the extremes of this distribution, we see tumbling. If we were to project this point cloud into the XY plane, which is what's shown here at right with the 50-degree geometry data added, we note that this the magnitude of this adder shows a strong correlation with tumbling cases, and that the larger adder and therefore a larger roll rate is required for the 50-degree geometry, which is nominally more stable to tumble. So a conclusion here is that the subsonic tumbling that is occurring is largely driven by the hypersonic interaction of mass and aero assumed uncertainties, which leads to these high induced roll rates. And that if there's a way to, through tested analysis, reduce the magnitude of the applied uncertainties, that may reduce the instances of tumbling observed in simulation. Next slide. So we know that a roll rate is a necessary but not sufficient condition for tumbling. So the question is whether there's a way to predict for a given vehicle configuration, will it tumble for a given roll rate? And ideally, we want to do this with a manageable set of inputs. Literature search revealed work by Peter Jaffe at JPL, who studied this problem in the late 1960s, particularly for drogeless entry on Venus. And his work, the result of his work was an analytical stability criterion based on a simplification of the equation of motion for terminal descent. We can move to the next slide. So Jaffe's full derivation is presented in reference 5 below, but I'm going to kind of jump in midway here and begin with an expression that he derives for the total angle of attack envelope during terminal descent, which is given in equation 1. And what we want to focus on here is that the total angle of attack envelope is modulated by an exponential term with an integrator in the argument. And Jaffe focuses on the integrand here and notes that with the assumption of an exponential atmosphere, it can be written as shown in equation 2. And we note that when this term is positive, the exponential has an integrator with a decaying argument, right? It has a monotonically decreasing negative argument, and therefore the angle of attack envelope will be bounded. And so Jaffe proposes this set of terms as a criterion for stability in angle of attack oscillation. So if we move to the next slide, what we can gain a little bit of insight into the predicted physical behavior by examining the parametric dependence of Jaffe's criterion. Note on the notation used here, P naught is our non-dimensionalized roll rate, and the naught indicates that it's taken at a reference altitude at the end of our dynamic pressure pulse. So we note that as our green term here, I've color-coded the terms just kind of for explanatory purposes, goes from 0 to 1 as the roll rate increases, and it modulates the terms dependent on this red term here. For low roll rates, the blue term is dominant, and we see a strong dependence on coefficient of drag, but also on pitch damping coefficient in Cn alpha. As this green term approaches unity, the blue H bar and red H bar terms cancel, and we see a strong dependence on Cn alpha and coefficient of drag, but the dependence on pitch damping actually cancels out between these two. So we would expect it to reduce with increasing roll rate. And that's kind of an insight we'll examine a little bit more closely. But one of the main notes here is that this analytic formula is a function of only a small subset of subsonic aerodynamic and mass properties, which means it can be evaluated relatively quickly for a variety of vehicle configurations. Next slide. So the first application here is a validation filter, and we want to see whether results trends are consistent with the 6 degree of freedom simulations predicted by Post. On the y-axis here, I have the Jaffe criterion plotted versus roll rate on the x-axis. And here I'm considering roll rate at 25 kilometers, which is our reference altitude in this case. And we note that we predict instability for a 6 degree geometry at about 90 degrees per second roll, which is consistent with the 6 degree simulation results. And we predict instability for the 50 degree geometry at approximately 230 degrees per second. Also, close to the values predicted by 6 degree of freedom simulation. For the nominal 45 degree geometry, no tumbling cases are predicted, and we see that the 45 degree remains constant for the highest levels of roll rate predicted in the simulation. So with the knowledge here that this criterion is predictive, we can look at how we can use it to inform design sensitivities and quantitative analysis. Next slide. So this chart is a little bit busy, but the main takeaway here is that we see variation in sensitivity to different parameters with increasing roll rate. In particular, we see an increasing dependence on coefficient of drag and CN alpha, and a decreasing dependence on pitch damping with increasing roll rate. And we can use this to kind of perform quick design sensitivity studies to understand qualitatively how we would expect stability to change with variation in vehicle configuration. So if we move to the next slide. In particular here, we look at sensitivity to mass. So for the 45 degree geometry, we look at configurations involving the max estimated value of mass, as well as the current best estimate mass, which is expected to be lower. And we note that with the CBE mass, that is all other parameters but mass held constant, we see a decrease in the roll rate at which we expect tumbling to occur, reduced by about 100 degrees per second. So a reduction in stability margin. And this is useful in that it tells us how we might expect design to vary from the standpoint of dynamic stability with variation in vehicle parameters. Next slide. So a few conclusions from this work. The observed tumbling in MSR EEV simulations is driven by the interaction of configurational asymmetries. And more detailed study may generate evidence that justify reduced uncertainties. A multi-fidelity approach here can be beneficial. So the Jaffe criterion can be used to supplement some of the information gained from 6 degree of freedom results. Obviously, it's much less accurate than a 6 degree of freedom simulation, but it is computationally inexpensive, and it provides this indication of stability margin, which is a little bit more difficult to gain from dispersed Monte Carlo simulations. It can also guide us in the ways that design modifications can affect or improve stability. And finally, since tumbling occurs subsonically, robustness against tumbling can be examined in full-scale testing, specifically through drop testing of articles at the credible bounding roll rate and CG and aero vehicle configuration. And if we check whether tumbling is observed there, we would expect that we can provide a strong validation argument from the standpoint of stability. So that concludes my presentation today. We can go to the next slide, and I'm happy to take any questions at this time.
Thank you, Jacob, for that great presentation. It's a fascinating area to understand better. I have some inside knowledge having worked EEV a little bit myself. Okay, so we have time for maybe one question here from Raj. I have, what steps, ground tests, can we take to verify the roll-yaw coupling of the MSR Earth entry vehicle at hypersonic speeds and limit its impact for low-speed landing risks? Do we need to go to a flight test for achieving confidence?
Yeah, and so I think that is the kind of the key question. And obviously this is something very difficult to test because the interaction is occurring hypersonically. I think there are some ways in which analysis can be used. I think this might also kind of address Carl's question. In, for example, TPS recession, we would expect potentially asymmetric ablation to be one of the factors that causes uncertainty in aerodynamic factors. And if we can bound that through analysis, there's reason to believe that if that's lower than the uncertainties we're applying, there's potential to reduce those values. But it's certainly difficult because it's difficult to test.
Okay, great, thank you. We're out of time, unfortunately, so if you have a minute to answer, I think there's another question in the chat. Maybe you could answer it via chat, that would be great.
Yeah,
thank you again, and we're gonna move on to our next presentation. Okay, so while that's getting pulled up, let me introduce the speaker. So this presentation will be given by Sierra Loma, who is a graduate student at Montana Tech studying geophysical engineering. She has been working on the UTTR, or Utah Test and Training Range, image processing project as a NASA intern since the summer of 2020. Her concentration is in remote sensing and UAS sensor development. So with that, I will turn it over to Sierra.
Great, thank you. So I'm Sierra Loma, and I'm going to be talking about the Utah Test and Training Range hazard database creation for Mars sample return. So next slide, please. An introduction, going over a little bit about the Earth entry system for NASA's Mars sample return mission. It is a small entry capsule that transports the Mars sample from the Earth return orbiter to the Earth's surface at UTTR. It lands at UTTR without a parachute at velocities greater than 40 meters per second or 90 miles per hour. It is designed to protect the Mars samples for landings on either the soft UTTR playa soil or from man-made objects or hazards in the landing area. So part of ensuring that the Earth entry system lands safely is finding any potential hazards it could land on. So the objective of this image processing work is to develop a map of hazards in the UTTR landing area that can be used to derive the probability of the EES encountering these objects. So you can see some of the pictures of the potential objects that we could land on in UTTR. There's some target darts, some structures, and other miscellaneous man-made materials in the UTTR. Next slide, please. Okay, the UTTR images are really high-resolution aerial photography of the south range of the Utah Test and Training Range. The resolution is up to 15 centimeters, so you can get really high detail from this imagery. They are RGB images, so just red, green, and blue bands of any standard photography. And these images are what I used for the image processing. I used a combination of Eridas Imagine and Esri's ArcMap to identify any potential hazards. You can see on the right, that's the entire survey area. So the black outline shows the UTTR boundary, and then that is all the imagery we have. And then on the left, you can see we have a fishnet grid. That grid was created to help us organize all of our hazards in the area. So each grid has its own name, and they are 1 kilometer by 1 kilometer square. You can also see those red ellipses are the initial landing area for the Earth entry system, so that's the focus of my image processing. Next slide, please. Okay, here are the steps I went through for the image processing. First, I did RGB clustering and RGB grouping, so you can see the original image of 2 target darts. Moving into the top right image, that is the RGB clustering results. I'm going to be going over all of these images more in the following slides. Then from those RGB clusters, I create polygons and go through all the polygons to check them for hazards. Then I add a buffer to the outside of all the hazards. And then I catalog all of the points and put them into the hazard database. And I take a picture and save every single hazard picture into the database as well for future reference. Next slide, please. Okay, so the RGB clustering and RGB grouping is done in Hexagon's Eridas Imagine. I use the RGB clustering tool, which produces grouped pixels that share similar spectral signatures. So the software looks at the red, green, and blue bands of the imagery and puts similar pixels into their own classes. From this, I use the grouping tool to pick out all these classes that could be potential hazards and then save them into their own layers. That way I can go into ArcMap and look through all the hazards. So next slide, please. So in ArcMap, I take all of those grouped classes that I found from the RGB grouping, and I go through them all individually. So you can see those red polygons in the images. That's what is produced from the RGB grouping. And so I go through every single polygon and see if any of them actually correlate to potential hazards in the UTTR. A lot of the time they do correlate to target darts or any other potential hazards. Sometimes there are vegetation that get picked up in the images as well, so I just go through those and actually see which ones are hazards. Next slide, please. Okay, after I go through and I find all the potential hazards, I add buffers to all of them. So using the buffer tool in ArcMap, I can add a extra area around each object. And the reason why we do this is to account for the diameter of the EES. We use 0.75 meters for all objects to account for the radius of the Earth entry system. And then for target darts that are standing up out of the ground, we move it up to 1.25 meters to account for that horizontal velocity. So you can see some examples, the target darts with those buffers around them on the left. The top right, you can see some aircraft wreckage with the buffer around it. And then the bottom right, you can see some more miscellaneous objects like tires and other structures, all have those buffers around them. Next slide, please. Okay, now for the hazard database format. Basically, I go through and I assign all of these hazards into this hazards database. And mostly what we need for the probability assessment is the X and Y coordinates and the area of the hazard, so how big the hazard is. But we also include what grid it's in, the type of hazard it is, all of the areas of the buffer around it, the actual object area. Each hazard has a unique ID and any notes that make this hazard stand out. That way, if we need to reference any of this in the future, we have it all done and ready. Next slide, please. So at this point, since each hazard has its own individual ID, I go through and I take a picture of each one with its ID in the picture. So you can see those target darts have S22_2, so that is its hazard ID. And every single object will have its own ID and picture associated with it. So those are the target darts, the aircraft wreckage again, and then there's a pile of tires there as well, as an example. All right, next slide, please. Another area that we had to look at was the southeast section of the survey area that contained a lot of built-up roads. These roads, a lot of them are made up of gravel and are a potential hazard to the EES as well. So I went through and I created individual polygons to make up the roads. There are over 16,000 of these road polygons, and I used a combination of manual and automatic methods in Esri's ArcMap to make them. So you can see in this picture, it looks like they're just red lines making up the road, but when I zoom in, those are actual individual squares. And the reason we needed these individual squares is because it makes it a more accurate probability calculation. Next slide, please. Okay, so to create these road polygons, I started by just going in and drawing straight lines on all the roads in ArcMap. This is pretty easy. Most of the roads are pretty straight and linear, so it didn't take very long. After that, I went through and I measured how wide all of these roads are and then segmented all the lines according to that, so that I would be able to create squares based on how wide the road actually is. So you can see in the right figure, all the different colors are all the different segments of that line. Next slide, please. Oh, I think we skipped one. Go back one more. There we go. From there, I used the same tool that I used for the previous hazards. It's the buffer tool, and it basically just creates a polygon on either side of the line. So you can see that in the left image. And there were some areas where lines were intersecting or the road was very curved and it didn't fit quite right. So then from there, I would go in and manually make adjustments so that all of the road polygons were fitting relatively well. So you can see that in the right image. Okay, next slide, please. So here are some more examples of the roads. You can see there's a runway in the top right image. Bottom right, there was a lot of adjustment on the shoulders and whatnot of those roads and the intersections. And the bottom left, you can see that triangle gravelly area. I just went in and manually created those polygons to make sure we accounted for any extra gravel. Okay, next slide, please. Okay, so that is a square area that was also near the roads that we wanted to create individual squares in. And we wanted to create 10 by 10 meter little squares inside of this large one. So this is just showing that process, outlining the area, creating a fishnet grid, and then cutting the fishnet grid to fit in the shape of that outlined area to make sure we're accounting for the entirety of that area in our probability assessment. Next slide, please. Okay, so that is all the processes that I have been using to develop this hazard database. I'm now going to show you some of the results that we've got from this hazard database. And I'd like to thank Ben Tackett. He is the one that's been working on this part of the probability assessment using the hazard database. So the hazard locations and areas are used for determining the probability of impacting a ground hazard during the Earth entry vehicle landing. So utilizing the Mahalanobis distance, we can predict the Earth entry system landing distribution and analytically calculate impact probabilities. We can determine the optimal landing location to minimize ground hazard impacts for a variable landing distribution subject to local constraints. So you can see in the left figure, it shows the red line is currently where we have the red ellipse I showed previously. If we were to target it there, that is the hazard impacts that we would encounter. If we moved the ellipse to have the minimum amount of hazard impacts, it moves down to the blue line. And then if we remove the 10 most likely to hit objects from the area, it moves again down to the green line. We can also evaluate worst case probability scenarios, like impacting a road along one of those ground tracks. You can see in the right figure, this is that such case. It is the maximum road impacts that you could get would be where the red ellipse is. So we can determine the worst possible place we could land using this kind of data. And those are some of the results. And if anyone has any questions, please feel free to ask.
Okay, thank you, Sarah. That was a very in-depth presentation on the work you're doing there. So it looks like we have a few questions in the chat. So let me go through these. So the first one is from Raj. Is there a way to do this through machine learning to do what you're doing? So he's asking if we can replace you with a robot, I guess.
It's probably possible for some of the hazards at least, but because we want to look so closely at the hazards, and a lot of them are pretty similar to the background soil, just the spectral signature is pretty similar. We want to make sure we're finding all the hazards. So if we did use machine learning, there would still definitely be a lot of manual components, I think, as well.
Okay. So next question is from Ralph Lorenz. It would be interesting to compare the feature list with radar images, for example, to benchmark the prospect of detecting probes on the Venus surface. Will the database be made publicly available?
I'm not sure about publicly available. I know we are working on a NASA technical memorandum that we are going to publish about this data set, so definitely look out for that.
Okay.
That's a good question. There are some larger hazards in the area. Most of them aren't where we are looking at specifically landing. I guess part of this project is seeing if we do need to remove any hazards. Since This probability calculation calculates the probability for each object individually. We would know which ones are most hazardous to the EES. And so if we needed to, we could go out and we could remove those.
Thank you, Sarah. I think we're about here. That was a great presentation. Okay, so this wraps up the first part of our session today. So we're going to take a short break. We're about 5 to 6 minutes behind schedule right now, but we had allocated 20 minutes for the break with the plan to play the poster presentations. So we have 5 poster presentations that Tim will bring up and play in sequence here for folks that have not had a chance to view them yet. And that will be followed by a poster session, question and answer period of about 15 minutes after that. And we'll try and stick as close as we can to that 20-minute after the hour time for the question and answer period. So as soon as the poster presentation is finished. So Tim, can you bring up the poster session videos? All right. Thank you. And we'll be back for more questions and answers at 20 after the hour.
And if there are some audio issues, these poster videos are also available on the sample return website where you registered, so you can also watch them without having Tim playing everything.
Tim, I don't seem to be hearing audio. I don't think it's, maybe we didn't try this before the session here.
Yeah, I suggest folks at this point just kind of look at the videos on the website themselves because, yeah, I think the audio is not coming through WebEx at this point.
Yeah,
this was a last-minute addition. Yeah,
I had it on full blast, but sorry, that's the best I can do right now.
Tim, I think it's music mode under the audio settings. I think I'll do it. Down next to your mute key, I think is where it is.
Tim, I think you have to bring up the settings from the down where your mute button is, and then there's a music mode button there, or checkbox you can select.
Yeah, in WebEx, not in Safari.
Yeah, I'm trying to see it right now. Unfortunately, it's at the top because I'm sharing. Let me see.
Control-Shift-M.
Oh, great. Okay. I'm on a Mac. Is that a Mac command?
I'm afraid that's the Windows PC that I have.
Now, the expansion tube is of interest because it can simulate the re-entry condition of a concrete tank capsule. But it is difficult to measure
looks like that worked. Thanks, Tim.
of the flow made by an expanded tube because of the short period, which is only microseconds of depth. This research measured heat flux around the 1/10th model of the Habitat sample return capsule in 6 to 9 km per second various flow using HEKX expansion tube at JAXA CC. Pictures on the left side of the middle section show the measurement system. We used the stainless steel capsule model, E-type coaxial SAM capsule, and an listener amplifier developed by this research group. And figures on the right hand show results of measurements. Measured temperature history is shown on the bottom shelf, and calculated heat flux is shown on the upper row in the figure. The test time was estimated for fast filter pressure data. Then these results and theoretical values were compared in figures on the bottom shelf. Theoretical heat flux at the stagnation point was calculated using Canberra's empirical equation, and the others are calculated using Green's theory. When short stroke 67 and short stroke 69 we failed to measure heat flux at 4 measurement points simultaneously. However, by comparing the results with the first measurement, it was found that the faster the airflow velocity, the more the measured and theoretical values tend to agree. The cause of it has not been clarified yet, but the accuracy of the assumption used to calculate the theoretical value may not be enough, or the noise shown in temperature data may be attributed to it. So more experiments and improvements of the model are needed to measure heat flux using HEKX in higher flow in the future.
Hello, I am Martin Stewart from on the Harvard study. The Harvard is the hypersonic air-rated technology solution enable use of European company solutions, which have different challenges to face. The biggest challenge is the cycle coming back from the open space.
Hi, Tim. I think you muted your WebEx, which killed the audio, unfortunately.
Sorry. The vehicle itself consists of two main components: the ERC, the capsule itself, which is filled with biosensors for aerothermal environment characterization, inertial measurement, and a parachute system for the recovery of the capsule. And then we also have the stage, which is basically a solid rocket booster with some basic GNC on it, which takes care of accelerating the capsule to the velocity required for the re-entry. The capsule mission is trying to launch from Europe. We can currently be involved with multiple launch vehicle providers, and we can use actually low-cost launch vehicle in order to fulfill the mission. After the completion of the mission, so the data will be analyzed, detected, and we hope to have in the future. Each sample can continue soon. Bye-bye.
Hi, I'm Aries Barrios, and today I'm going to be presenting some current work that I've done comparing using different surface site densities and oxidation models applied to carbon composites in hypersonic environments. So it's important to understand the oxidation process that happens on the ablative heat shields that are commonly used on hypersonic vehicles like reentry probes. The surface oxidation models rely on the reactive site density on the surface. However, obtaining these site densities is not a particularly trivial task. And so the current aim of what we're looking at is the effect of changing the site density definition in the chemistry models and seeing the effects it has on the heat flux to the surface. So in our current work, we've simulated a 8-degree half-angle nose cone in a 40-kilometer environment with a free stream velocity of 7 kilometers per second, and we've applied a radiative equilibrium boundary condition on the surface of the nose cone. Using the results from that base solution, we start to apply the Leary surface oxidation model, and we apply with 3 different surface site densities, 10 to the negative 3, 10 to the negative 5, and 10 to the negative 7 sites per meter squared. So from the preliminary results, we don't see much of a difference between 10 to the negative 7 or 10 to the negative 5 sites per meter squared, but we do start to see a difference once we get to 10 to the negative 3 sites per meter squared. You can see some differences between the mass fractions along the surface for sure and in the flow, and you can see small differences between the surface temperature and the heat flow as well along the surface. We'd like to utilize the surface oxidation model in order to model the actual surface recession experienced during ablation cases and observe the differences that defining a different site densities makes on the entire process. I'd like to take a moment to thank the Air Force for their continued support in our research endeavors. And that about wraps up what I have to present today. Thank you for listening, and I'll stick around for any questions.
My name is Maria Stackpole from NASA Ames, and this poster is on the extensibility of PICA for future sample return missions. So PICA is a state-of-the-art low-density carbon phenolic ablator. It was first proven on Stardust, and since Stardust, it has successfully been used in MSL and most recently in Mars 2020, both in a tiled configuration. OSIRIS-REx was a build-to-print Stardust, and that was a single-piece heat shield. In around 2016, the heritage rayon used in PICA stopped production, so we had to identify a replacement, and we identified lyocell as a viable source. Lyocell is a sustainable, environmentally friendly domestic source that can be used to manufacture carbon fiber foam. Lyocell also is manufactured in multiple factories in the US and Europe, thereby alleviating a supply chain concern. So once we identified the lyocell replacement rayon, the next step was to go ahead and fabricate material and complete some testing. Initially, we completed some thermal and mechanical lot acceptance testing. All of the property data from the lyocell PICA was very much in family with previous production rayon PICA, and the data is well within spec limits required for flight hardware. We've also completed some ArcJet testing to evaluate thermal response, recession, and for the given test conditions in both air and nitrogen, all the results indicate that the recession and in-depth thermal response between the lyocell-derived PICA and heritage rayon-derived PICA are very comparable. We also scaled up the near-net shape single-piece PICA production from a 0.8 meter OSIRIS-REx or Stardust scale to approximately 1.5 meter single piece. We completed non-destructive evaluation to ensure no anomalies, and we also converted one of the units to a 1.4 meter Pika heat shield. So this effort, there were significant lessons learned, and these have led to substantial risk reduction for single-piece heat shield manufacturing. In summary, Pika is a workhorse TPS for NASA, establishing and extending the capability of Pika, including scale up to 1.4 meter, will allow sample return missions with higher entry speeds and larger future payload capability.
I think, Tim, if you want to close I think the playlist is over now.
Great.
So Marcus, are we transitioning to Q&A, or is there still a little time left on break?
Okay. Yeah, I think the plan was to transition to Q&A as soon as the posters were done, since we had run a little late there. Benoit, were you going to run the Q&A session? Are you on?
Yeah, sure. I can start on the Q&A session. So thank you, Tim, for playing those. And as Marcus mentioned, we're going to move into a Q&A session on the posters for about 15 minutes before resuming the oral talks for the rest of the session. So I see there's a few questions on the chat. Feel free to add more questions as the session progresses. I will read them as they come along. Okay, so let's start with a question for Tammy Kondo from Sam. So the heat flux measurement of Hayabusa capsule Earth re-entry. So how would this uncertainty in heat flux translate to a difference in the required TPS thickness? That's the question to Tamami Kondo.
Okay. Thank you for the question.
So the question was, how would this uncertainty in the heat flux translate to a difference in the required TPS thickness?
I'm sorry. I don't know what
So in your poster, you mentioned some uncertainty in the heat flux, and so how does that play with the TPS? How do you include that in your TPS thickness calculation? Okay, that's okay. I can give you a chance to think about it. We can jump to a different question and.
Sorry. I still don't understand what TPS thickness.
That's okay. We can come back to you if you have a chance to think about it, and we can jump into the next question. I'll come back to you later. Okay.
Okay.
So we have a question to Ares Bios-Lobel. Are the reaction sites typically uniformly distributed on the surface? So can the density be linked with any critical steps during the fabrication process? And that's a question to Ares.
Hi. Can you hear me?
Yeah.
Okay, good. So usually, at least to my knowledge in the simulations, you kind of like assume it's uniformly distributed. But I'm not super familiar with the whole fabrication process. So I'm not sure during what step during that process you can determine that. It's a kind of like a complex situation to try and figure that out. The current assumption of using 1×10⁻⁵ sites per meter squared, for example, comes from an assumption that it's just kind of like a perfect sample of graphite. I'm pretty sure that's the best that I could answer that.
Okay, thank you. And if I can add to the question, how does different density compare to current technology or current materials that we have?
How does different surface site densities, how they compare? I'm not sure I understand.
Well, is there any current technology you following those numbers, or are they for a new type of technology, a new type of material?
So this is again for carbon surfaces, right? So if you want to compare to other materials, that's going to be a different examination process, as well as the chemistry model may not necessarily apply. Yeah, not sure how you would want to approach that from the top of my head, anyways.
Okay. Yeah, that's good. Yeah. Okay, thanks. Looking at the list, we have a question for Meret. Sorry, I'm maybe mispronouncing your name. So Meret Stakpur, do you feel that the 1.4 meter single piece size achieved with Pika is near any possible intrinsic limits for this material?
So the 1.4 meter was chosen, the limiting factor at the time was the infusion vessel, so that was the conversion to Pika. That is something that definitely could be scaled up. However, if we're looking at the wet casting of the fiber form, at the 1.4 meter, the handling and support tooling to stabilize that wet cast was becoming more challenging. You have to take it through the drying step, ensure there's no cracking. So we are probably approaching a limit. And I guess also the other thing that needs to be thought about is the bonding operation as you scale up a single piece Pika, because it is a very low density and somewhat fragile material. So hopefully that answers your question.
Yeah, thank you. We got a question for Somakawata. How big is the interrogation volume on FLDI? Is there any effect from the beam path, or is it simply a few millimeters near the focal point?
Okay, thank you for the question. Can you hear me?
Yes, we can.
The length of the FADI is about 10 meters. This length has no direct effect on the measurements. The central sensitive length is directly affected. Okay.
Okay, thank you.
Yes, thank you.
So following, we have a question for Martin Sudars. What G-loads are reported by the kick stage and the launch, and how does that affect the system design for the later entry instruments? So when the loads are in the opposite direction.
Yes, the maximum G loads we can get is 70 G. We can arrive at 70 G maximum, 70. For the second part of the question, actually we didn't get into the details, and we need to in the next phase of the study. There will be.
Okay, thank you.
You're welcome.
So we have a question back to Meret Stackpool. What additional testing of PKD is still in the pipeline?
Yeah, so our ArcJet testing was delayed this past year. We just weren't allowed access on site. So we have a series of ArcJet tests to complete in July, August timeframe at Ames. And also we're working with our partners at Fiber Materials Inc. to complete lot acceptance testing on a series of billets that were recently processed. So there's additional thermal mechanical testing and also additional ArcJet testing to be closed out by October 1.
Okay, thanks. Maybe we can come back to Tanami Kondo. Do you have a chance to think about the question that we asked earlier? So what's the relation between the heat flux and the thickness of the TPS? So because you mentioned there is some uncertainty in the heat flux, how does that translate into a difference in the required TPS thickness?
Okay, and at this time we don't know how this will affect the thickness of the TPS. We need to do further experiments to get reproducible results to know required TPS thickness.
Okay, thank you.
Thank
yeah.
you.
I might throw in another question for yourself, Tamami. So in your poster, can you explain why the heat flux was twice as much as what the theoretical value predicted? So you mentioned you test, you end up with a heat flux that was twice as expected. Can you explain a little bit there?
You mean the causal difference between experimental and theoretical value of heat flux?
Yes, that's right. That's okay. Don't worry if you don't know on this.
The cause is not have been clarified yet. but the assumption I used for calculating the theoretical value maybe not accurate.
Okay, I see. Okay. Well, thank you for your answer. If there is no more question on the chat, then I suggest we move on to the next set of oral talk. Okay, so we will restart. So we have 4 more talks in the lineup, and we will start with a talk from Rosemary Besnier and Gregory Pinault. So let me just give you a quick intro. So Rosemary is an Equipment and Service Program Manager after a master's degree in Composite Materials Behavior from École Nationale Supérieure des Arts et Métiers in 1999. She joined Ariane Group, where she manages a feasibility demonstration in high temperature composite materials for space programs such as heat shield, RTG, electric propulsion, as well as for other industrial sectors. And then it's going to be a double talk with Gregory Pinault, which is an expert in thermal protection systems at Ariane Group since 2016. He's in charge of atmospheric reentry projects as thermal protection architect. He's currently leading thermoablative modeling and experimental activities for advanced thermal protection material. Please, the floor is for you.
Okay, thank you for the introduction. So next slide, please. Again, one next, please. Yes, again. Yes. So I'm going to just give a few words about Ariane Group. In fact, Ariane Group have been built on the experience of two mother companies, Airbus Defence and Space and Safran, by joining the atmospheric reentry technology and also solid propulsion technology. Next slide. This slide gives a short overview of the different projects in which Ariane Group were involved through Earth atmospheric reentry demonstrators up to some exploration in Titan with Huygens and also with Mars with the Schiaparelli probe capsule. We have more than 40 years experience in a reentry system and development technology, from simulation, from qualification of materials up to the design of our own plasma torch and ground testing capabilities. Next slide. We have also a large portfolio of ablative materials, but non-ablative materials we'll see after. From low density on the left hand side you can see pica-like materials, which are Astium materials, up to very high density materials and with high capabilities of resistance to high heat loads. And on the y-axis you have the different tier of this technology, which were flown for several of them. Next slide.
We also have a long-lasting experience in the production of the 3D carbon and carbon composites with carbon reinforcement for carbon-carbon, carbon silicon carbide, and carbon phenolic composites. In the launcher market, we are selling a CC nozzle extension for the US market and also for the European market with the launchers, the family Ariane 5 and 6 coming, and Vega. And we want to point out that on the Vega, we are currently producing 3D composites, carbon phenolic, the same as we are speaking about today. Next slide, please. We have huge manufacturing capabilities for producing parts in composites, carbon-carbon and carbon-phenolic one. We can tune the thickness of the parts from 2.3 millimeter up to 80 millimeters, depending on the application target we have, of course. And we have capabilities, processes capabilities to make parts with diameter up to 2.1 meter. Next slide, please.
One second. Yes. One. Again, based on these two complementary heritage, we decided to develop a new TPS based on the common fibrous complex to address two different types of high-speed reentry mission. So on the first type of mission that would require the carbon phenolic materials, typical Earth reentry sample mission, and the second would be related to ice giant exploration, like Neptune or Jupiter. And this one would require higher density materials and with carbon reinforcement and carbon matrix composite. For the ERC and the Earth reentry capsule, we considered a 45-degree cone angle aeroshape with a 1 meter diameter capsule and the entry velocity less than 30 kilometers per second, which was selected accordingly to the heat flux constraints, J load, and pressure at stagnation point. The maximum heat fluxes here was derived from the maximum known criteria for ASTEM, the lightweight abattoirs. And for this kind of mission, it's typically around 15 megawatts per square meter, but it's not a limiting criteria for the 3D carbon resin. For the exploration of the ice giants, since the entry velocity was very much higher, around between 23 and 35 degree for a flight path angle of 35 degrees and the entry velocity of 23 kilometers per second, the heat fluxes is much more larger, around and is larger than 70 megawatts per square meters, mainly coming from radiative contribution, but depending also from the different species like methane in the atmosphere. And the maximum total pressure is much more larger than for Earth reentry mission, like around 8 bars. Next slide.
Speaking about the properties of our 3D composites, and especially the carbon phenolic one. As I said previously, it has a high maturity in production because we are still currently use it for Vega and for some components in nozzle. What is important to say is that it's a common fiber architecture in carbon we use for either the organic infusion or the carbon densification. So this is a material which is high sustainable in production, I would say, in the industry. And the 3D fiber architecture, which is obtained by needling process, I will speak about just after, gives to the composite higher properties in thermomechanical, thinking that we have no need of bearing structure if we are using this 3D composite for the shield, and it gives a high mechanical performance and especially no delamination at cooling. Next slide, please. Speaking about the process now, next slide, thank you. The needling principle is to transfer carbon fiber in the third direction from a carbon mat reinforcement by needles that are small harpoons. You can see that on the left hand of the slide. We have the process internally to make carbon mats plain parts or cylindrical parts. And regarding the matrix, we have two processes. One is the CVI, the chemical vapor infiltration, for carbon-carbon or carbon-silicon carbide composites, we are able to tune the density of the carbon-carbon from 1 to 1.8, depending on the target we want for the application. And regarding the composite carbon phenolic, we use infusion process. And here also, we are able to tune the density from 1 to 1.4. Next slide, please. We have made some improvements in the technology, in the needling process, by finding the way to manufacture a heat shield shape in one piece by a robotized needling process. You can see the process on the left of the slide. The idea here is to improve this technology to be able to make really one piece. This was part of the scope of the contract. If you can go next slide, please. Next again. This contract is in the scope of the contract named pre-head for preparatory activities for heat shield development that we have with ESA from now more than 1 year. And last year in 2020, we demonstrate the possibility, the feasibility to produce a single piece 3D carbon reinforcement that you see in the picture in the middle of the slide, and demonstrate that we can raise a thickness of 60 millimeter, a diameter of 1 meter, with a nozzle angle of 45 degrees, which is the most challenging one. We are able, of course, now to produce 45 degree or 60 degrees if needed, and a nose radius of 300 millimeters. This is the carbon-free form that is homogeneous and seamless material. We will, in the coming weeks, make the infusion on it to raise a density of 1.3 for the heat shield itself, and on a spare part 1.4 to be able to make some elementary testing on both densities. And as it is seamless material, we assume there is no need of flight validation, but only elementary testing, speaking about arc jet and hypervelocity impact testing that we will explain just after. Next slide, please.
Yes, considering the testing of this material and the characterization of the behavior, we managed and we had the opportunity to test to use the most powerful electrical arc-heated plasma generator we own at the Ion Group, which is 20 megawatt plasma torch on a wedge configuration. One of in fact, the top face of the samples is the closing face of the nozzle, and at the maximum stagnation point, we reach 18 megawatt per square meters with a pressure of more than 4 bars during 25 seconds, which makes a huge deposition of energy compared to the requirement of the reentry demonstration. We observe, as you can see on the picture in the middle, that the roughness of the surface after the test was very close to the 2D tilt layers materials with the carbon with the standard reference materials, and we reach also the same ablation compared to this reference materials.
Next slide, please. We also made some hypervelocity impact testing in the Fraunhofer Institute EMI at Fribourg, Germany, with an average impact velocity of 7 kilometers per second. We provide 4 plates. 3 plates were with a thickness of 15 millimeters, with the aim to determine the ballistic limit of the material. We would change the dimension of the projectile. You can see it on the table in the middle of the slide. And we find then hole, no hole, to find the limit, the ballistic limit. And we made one more test with a plate with a thickness of 30 millimeter, which is more accurate for Earth return missions. On this one, it's the sample you see under the video. We had an impact, a crater, and we machine a sample that will have now a test, a stagnation point plasma test at 13.5 megawatt per square meter in DLR, Germany during the summer to address the ablative behavior of the material once it's impact. And you can see the video on the right side of the slide. Next slide, please.
Yes. Moving from the material to the wall probe capsule performance assessment, we managed to have a comparison of the performance of these materials compared to the state-of-the-art configuration for an ASTEM and a low density ASTEM ablative materials. On the left-hand side, you have the standard configuration which needs a CF30 mechanical bearing structures plus an ASTEM as ablative materials. And on the right-hand side, you have a typical configuration that we propose that is possible to get with the 3D Mexico resin. That, as Rosemary said, we don't need any load-bearing structures since it's a thermostructural materials. And we just need insulation layer inside to get the same performance, the same thermal insulation performance than the state-of-the-art configuration, but with the same mass budget. For this type of re-entry scenario, we get a near net shape aero shape with this material without seam. And it's a monolithic heat shield. With the same configuration, with the same performance, we get also we managed to increase the internal volume with this 3D Mexico resin, and with the advantage to have higher ablation, lower ablation for the Mexico resin, and higher resistance to the MMOD thread. Next slide.
And next and last slide. Just to give you an idea of the time, the notional schedule of the development of such a part, starting from the requirement we can receive from any Earth return mission, we are able in 1 year to develop the design of the heat shield in Mexico resin, as Gregory and I said just before, and freeze the design after 1 year, and then have 2 years of industrialization and manufacturing to be able to deliver the items either for characterization and flight model items. Thanks for this time. Yeah, and if you have any questions, we can.
Okay, thank you very much for this interesting talk. Maybe if we have time for a quick question. So I see there's a question on the chat from Ishii Sakraker. On slide 17, so which plasma facility did you use?
Yes, it's in Cologne.
17. I think it's 200. This target is the standard target we can use in ion group. It's the most powerful, around 20 megawatts per square meters, and we have in fact a full torch that gathering and mixing together the plasma in the mixing chambers. And at the exit, we can have either wedge configuration like we tested for these materials, or either stagnation point configuration with, of course, higher pressure and higher expertise. But it is on a smaller samples.
Okay, thank you very much. I think we will move on to the next speaker. So next we have Marco Rotondi. So while the slide is popping up, let me just describe, give a bit introduction. So Marco Rotondi is a PhD student in aeronautical and space engineering at the Department of Mechanical and Aerospace Engineering of University of Rome La Sapienza. His research activity is mainly in computational fluid dynamics with gas surface interaction, modeling for rocket propulsion and atmospheric re-entry application. So please, Marco, we listen to you.
Yes, thank you, Benoit, for the presentation. Can you hear me?
Yes, we can.
Okay, thank you. So I'm going to present you the work numerical analysis and flight relevance verification of low temperature radars undergoing shape change, and this work has been carried out from a collaboration between the University of Rome La Sapienza and the von Karman Institute for Fluid Dynamics, and it has been funded by the European Space Agency. Next slide, please. So the work is mainly focused on the ground testing of ablative materials for re-entry application, and this is usually done in plasma wind tunnel facilities. But in this kind of facility, it still exists sometimes a substantial difference in the flow around the test article in terms, for example, of the Mach number or of the chemical composition of the flow. And this may alter the ablation and the shape change of the capsule. So a possible solution is to use ballistic shock tube wind tunnels where the flow conditions are more similar to the flight ones. But in this kind of facilities, we have a limited test duration of the order of milliseconds, which not allow to obtain the ablation of the H shield. So to overcome all these limitations, a possible solution we are looking for is to use low temperature ablators in a low enthalpy hypersonic wind tunnel, and this allows potentially to perform ablative tests with relevant shape change. And in this context, the goal of this study is to present the numerical results obtained from the simulation of these materials in hypersonic conditions, and to evaluate their shape change, and then numerically prove their flight relevance in terms, obviously, again, of shape change. Next slide, please. The test case we considered is the Phoebus capsule, which is a sample return mission under investigation at the European Space Agency. The full-scale capsule employs a graphitic H shield, and it has been simulated in this work under the actual flight condition, while we also simulate a subscale capsule employing a camphor-based H shield. And the condition we consider for the simulation of this subscale camphor are those of a test campaign carried out under the H3 hypersonic blowdown wind tunnel at the von Karman Institute, and some photographs of this experimental campaign are shown below in the slide. Next slide, please. So from the numerical point of view, we use a CFD solver for the numerical simulation, which employ an ablative boundary condition, which includes some Fanny Waits effect for the surface reactions. But however, this CFD solver assumes a steady state ablation. So in order to include possible effects due to the heating transient, we had coupling with a 3D ablative material response code. And here below are reported the computational setup used for the simulation on the right for the material response code, and on the left for the CFD code. So next slide, please. So firstly, we carried out some on-ground simulation of the camphor subscale Phoebus capsule, which are shown here. In this first slide, we can see the shape change we obtained by performing subsequent CFD steady state simulation, so without the heating transient. And as it can be seen, the shape change effects are significant of both the shoulder and the spare core junction, as we can see on in the ablation mass flux distributions on the right side, which are largely changing in time, as we can see. And moreover, the nose radius is reduced in the experimental campaign by 23% after the wall exposure time of 30 seconds. Next slide. Then the CFD steady-state results have been upgraded by coupling with the material response code, and in this way we can get some information about the transient phase and also on the thermal penetration thickness inside the Cantor TPS. And in particular, as we can see in the figure, the thermal penetration thickness showed to reach the overall Cantor thickness in the experiment after just 6 seconds of exposure. And so this allows the interaction with the metallic support. Moreover, as we can see below, the transient phase showed to be quite important, especially for the erosion rate, which is shown on the right side of the slide, which approach the steady state after a large time of approximately 3-4 seconds. So we can say that the heating transient play an important role for the on-ground experiments. So next slide. This importance of the heating transient is even more evident looking to the comparison with the numerical results with the experimental data. Here we can see the comparison in terms of stagnation point recession. And in particular, in the figure, we have solid lines, which are the CFD steady-state results, while the dashed lines are the CFD material response coupled results. And it is evident how, especially in the first seconds, so in the zoom at the parts of the figure, we can see how the CFD material response coupling procedure allows to have a better agreement with experimental data. So highlighting again the importance of the heating transient even from the experimental evidences. So next slide. So then we analyzed the actual reentry of the Phoebus capsule, so using the graphitic heat shield. And in order to do that, we need to build a proper CFD test matrix, which allow us to cover the whole ablation window expected during the reentry. And so we had to reconstruct the Phoebus trajectory, and to do that, we use some ESA-declared trajectory points, which we use as 15 points of our trajectory, which are the black marked in the figure. And then we had some additional 3 points, which are the red marked ones. And the final result is the CFD test matrix reported on the right, where we can see how the flight conditions are largely varying in time, with a Mach number ranging from a maximum of 36 to a minimum of 5. So next slide. The strong variation of the flight condition is evident also looking to the flow fields obtained from the CFD simulation. And in particular, we can see how the shock standoff distance and shock intensity is largely changing from trajectory points to trajectory points. And on the right, we can see instead the evolution of the chemical species concentration in the shock layer along its initial line. And as we can see, we have a full dissociation of molecular oxygen and nitrogen for the trajectory point reported, and moreover, near the wall we can see the appearance of carbonaceous species produced for the ablation of the surface. So next slide. Here we can see the CFD steady-state results for the wall ablation window we analyzed. And in particular, these ablation windows show to last for about 19 seconds. Looking now to the heat flux reported on the left, we can see how the peak heating condition for the CFD results correspond to the trajectory point 3 with a peak heat flux of the order of 8 megawatts per square meter. In this figure, we have also we have solid lines, which are the CFD results, but we have also some dashed lines as well, which correspond to some semi-empirical correlation results for the heat flux, which are some correlation used by ESA in their preliminary analysis of the mission. And these semi-empirical results are in line with a fully catalytic boundary condition, so not with an ablative one. And this is the reason why they are overestimate the ablative CFD results. But however, it is important to note how ablation, as ablation is reduced at the end of the ablation window, so for the last trajectory points considered, the trajectory points 6 and 7, the semi-empirical and CFD flux start to be almost superimposed, and this is something we expected, and which confirms our results. So next slide. As done previously for the on-ground simulation, we coupled the in-flight CFD steady-state results with the material response code. And in the plots shown here, we have the red lines which refer to the CFD standalone results, while the blue lines refer to the coupled CFD material response results. So concerning the stagnation point, world temperature, which is the one above, qualitatively we have similar results, but about the exception of the initial focal phase. The same applies for the recession on below, but however, as we can see here, after the transient phase, the couplet CFD material response results show to overpredict the recession foreseen from the CFD steady state simulations. And the reason is the fact that the material response assume a chemical equilibrium at the surface, as classically done in material response code for the entry application, while the CFD assume a finite rate model for the surface reactions. However, the most important result for our study, which is focused on the flight relevance of the shape change, is obviously the shape change. Okay, and as it can be seen in the figure on the right, the final shape at the end of the ablation window is almost the same if we consider all the CFD solver steady state alone, or the CFD complex material response. So we can conclude that the heating transient plays some marginal role in the evaluation of the capsule shape change for the flight. So next slide. So finally, we looked to the flight relevance of the experiments with the low temperature ablator, so with camphor in this case, and in particular to prove the flight relevance of the shape change, we must prove not only the shape change similarity, but also the aerodynamics, so the pressure similarities, in order to say that the experiment is relevant to analyze the behavior of the capsule during the flight. So concerning the aerodynamic similarity, we compare the dimensionless pressure distribution obtained from the two set of simulation, as we can see from in the left and the figure on the left. And this is something expected in reality as we are in the hypersonic regime. So the aerodynamic similarity is almost perfect, but this is a consequence of the Mach independence principle, of course. But on the other side, less intuitive is the shape change similarity, which we checked by comparing the dimensionless ablation mass flux distribution. In this case, as we can see, the profiles are quite similar again, but we have some differences in the cone and the shoulder region, where the ground test overestimates slightly the flight recession of the graphitic H shield. Next slide. So we investigate this discrepancy in the cone and shoulder region, and we saw that it seems to be due just to a different Mach number. In fact, the ground test assumes a Mach number of 6, while the flight, during the flight, the Mach number, as we saw before, is changing. But if we consider a similar Mach number during in the ground test and the flight, the dimensionless ablation mass flux profiles becomes practically superimposed, as we can see here. And this is not obvious, as the materials used are quite different. In fact, we have camphor for the ground test, which is an only sublimating ablator, while for the flight we have graphite, which is an ablator which undergo not only sublimation but also oxidation and nitridation. So the chemical reaction occurring on the surface are quite different. So by looking to these results, we can finally state that we have both a similarity in terms of ablation and shape change, and this is good results for the research. So next slide. So finally, we looked just for ground test time, which is relevant in order to obtain the same relative recession we obtained in flight from the numerical simulation. And obviously, we have in flight 19 seconds of ablation window And for our ground test using camphor in the H3 tunnel, we saw that a time of just 1.4 seconds is sufficient on ground to obtain the same relative recession of the flight at the destination point. So when we figured out this time, we looked also to the full shape change, not only at the destination point. And as we can see in the figure below, the shapes are practically superimposed, considering the two different times, with only some little discrepancy in the shoulder region, which is something we expected as seen before for the different Mach numbers. So next slide. So just to conclude, some remark points. So in this work, a subscale camphor model of the Phoebus camphor has been numerically simulated and experimentally tested at the von Karman Institute. And we observed a significant shape change on the camphor model from the experimental numerical observation made. And moreover, the CFD material response coupling showed to be important, especially for the ground condition, where the transient space showed to play an important role. Then, concerning the full-scale Phoebus capsule, which used a graphitic edge shield, we have seen how, in this case, we saw a much lower relative recession than during the on-ground test. And moreover, in this case, for the flight condition, the heating transient effect showed to be quite marginal. And finally, we compared on-ground and in-flight results to prove the flight relevance of the low-temperature ablators. And the flight relevance has been proved by showing the similarity in terms of aerodynamic and shape change. And this allows us to conclude that the aerodynamic behavior and stability of a full-scale camphor, full-scale capsule made of carbon-based materials during the flight can be potentially estimated by on-ground test of subscale camphor made of low-temperature ablators. Thank you for your attention. I conclude my presentation.
Okay, thank you, Marco. Maybe a very quick question because we are a bit behind schedule. So there is a question from Luigi Cutroni in the chat. What is the material response code you are using?
Yes, we are using PATO, porous ablative thermal response code, which is an open source code developed recently by NASA. This allows to model not only as classical material response codes like CMA or others, a one-dimensional conduction and ablation, but it allows to have a three-dimensional modeling of the material response. And moreover, there is also the possibility to handle a 3D resolution of the flow inside the char layer, so the decomposed layer. So the char, the porous gas are free to travel and exit not where they are produced, but in another location. So it's a quite powerful tool.
Okay, thank you very much. So yeah, we don't have much more time for other questions. So let's go to the next step, which is Daniel Wang. So Daniel has a bachelor degree in aerospace engineering from San Jose State University and will continue pursuing his higher education in computational and mathematical engineering at Stanford University. Currently, he focuses on mathematical modeling and numerical integration of various complex dynamical systems and has experience creating advanced scripts in MATLAB. So Daniel, when you're ready.
Thank you. Can you guys hear me?
Yes, we can.
Okay, great. So I'll be presenting on the planetary descent using solid motor thrust vector control. Next slide, please. The biography was briefly gone over by the mediator. Next slide, please. So a brief overview of the presentation. So I'll go over the current technologies of thrust vector control descent and a comparison between thrust vector control between solid and liquid motors and then go into the requirements and considerations for solid motor thrust vector control. Then I'll go into a three-phase descent process, first phase being passive stabilization, second phase active control, and last phase landing. And we'll end off with Q&A. Next slide, please. So a brief history of retropropulsion. It has been historically used to decelerate large spacecraft in low-density atmospheres, such as the lunar lander on the moon. And also recently, the Falcon 9 from SpaceX has been used to land on Earth successfully. The primary method for doing retropropulsion and attitude control is using thrust vector control, TVC, and thrust throttling. But other methods are also possible, such as cold gas thrusters and momentum wheels. So the feasibility on those skills may or may not be as great as TVC. Presently, all of the attempts to use TVC for descent have used liquid propellant motors, and it is important to note the differences between liquid motors and solid motors. Next slide, please. So for liquid motors, they are known for the higher energy per unit mass, their reusability and throttleability, so they have a much higher complexity in the engine and plumbing infrastructure. They also have complex fuel slosh dynamics that can affect the dynamics of the system drastically and affect the stability of the system. In contrast, solid motors have a much more simple design, have a higher propellant density, but are unable to tune the total impulse after launch. And they're single use. Next slide, please. So we'll go into the descent process. Yeah. The requirements and considerations for solid motor thrust vector control. We'll start off with tolerances. There are some high tolerance regions, such as the PVC actuation, which need to be extremely accurate for the system to work. And other systems, such as the grid fin actuation, the landing leg actuation, don't need to be as high of a tolerance because they're not as mission critical. Other components, such as sensors, are also needed to create a solid state feedback control system. And the IMU provides the data for the position and attitude readings, which are provided by the onboard accelerometer and gyroscope. The altimeter can also be used to gather data on the altitude, which is also a very important parameter when landing a vehicle. Furthermore, you can also consider using GPS for higher precision on the positioning of the vehicle. The next component of consideration would be data, which would require a good enough processor to process all of the data at a reasonable speed that will allow for proper control of the system. And also, the data transmission or storage is necessary for diagnosis and model verification in iterating the design. And if transmission of the data is needed, a proper antenna will also be a key consideration in the design of the vehicle. And lastly, the manufacturability for smaller scales, for smaller scales such as model rocket scale. 3D printability and will be a key factor in what components you will be able to manufacture. Next slide, please. So the first stage in the descent process is the passive stabilization, and this can be achieved using various methods of aerodynamic stabilization. One of the most useful methods is to use grid fins, as shown on Falcon 9 SpaceX rockets, and as they can not only be used for stabilizing the center of pressure to be behind the center of gravity, they can also be actuated to pinpoint much more accurately the position of the landing site. And they can also have higher induced drag, which can stabilize the terminal velocity, which can reduce the total impulse needed for the rocket to slow down to zero velocity and land successfully. And that is a key consideration in what type of motor you choose. The grid fin deployment is mainly dependent on the altimeter readings, so it's not deployed during ascent or any other stage, and is most effective in higher velocity regions. Next slide, please. So the second phase is active control, with the goal of using thrust vector control to maintain an upright orientation. Some important aspects of active control are the thrust vector control gimbal, the thrust profile of the motor itself, and the total and excess impulse from the motor, and also calculated during descent. So the processor will need to take into account how much total impulse the motor has, and subtract the expected use of the expected impulse needed to slow the rocket and control its attitude, and that will result in excess impulse, which needs to be dissipated in a gimbal maneuver. And the first step for an active control would be to have an idealized control system with two inputs, 6 output, 2 inputs being gimbal angles, and 6 outputs being the states, the position and attitude of the vehicle. And there's several methods to achieve this. One being using linear quadratic regulators, which utilizes a linear system and approximates the rocket dynamics about an equilibrium point, with, in this case, vertically upright. The problem with this is that it will be only applicable to very small ranges of vehicle states, and can be unstable, can be not as accurate in higher perturbations. Therefore, quaternion control, which is commonly used in many spacecraft applications, can be used, and an example of this can be seen on the right for a simple satellite model. And that has the benefit of modeling the full nonlinear attitude dynamics of the system. The second phase of active control would be to implement additional noise and error compensation, some of which being electrical noise, mechanical tolerances, sensory noise. And that is important as that will shift the stability regions of the system, and that may or may not mean that you need to change the control system gains. Next slide, please. So the last phase is landing, with the purpose of keeping the rocket upright while experiencing the stresses of landing. And historically, the Falcon 9 and the lunar liner have used 4 retractable landing legs. And it is important that they're retractable in the descent phase so that it doesn't affect the aerodynamics of the grid fins upstream. And the grid fin design should be also keep in mind that the energy needs to be dissipated and not reintroduced into the system via springs. So damping forces are much better than spring forces in landing legs. Next slide, please. So our group from San Jose State has built a model prototype seen on the top. in CAD, and in the middle you have the electrical diagram with the IMU altimeter, the processor with a servo controller to help manage the actuation of all the servos, and also actuation ignition devices to actuate the grid fin and landing legs. And on the right, we have thrust profiles, on the top being the manufacturer specified thrust profile, and on the bottom being our tested thrust profile. And it is sort of different. And when calculating the total impulse from the motor, it is quite different. And that can, if not accounted for properly, it can lead to the control system severely underperforming, which can lead to catastrophic failure. And it is important to do these tests to figure out what exactly the thrust profile is, so that the control system can accurately know what power it has on the system. Next slide, please. Yeah, thank you. Any questions?
Okay, thank you very much. Please type any question on the chat so I can relate them to Daniel. While you're doing this, maybe I can start with a question. Are you using the grid fins as an active control system? I wasn't sure to catch that. And if so, how do you combine the fins and the TVCs? How do you proportionate between the fins and the TVCs for the active control system?
So for our project, we did not consider actuation of grid fins, but because of the complexity on the model scale. But on a larger scale, actuation of actuation of the grid fins would be important in pinpointing the location of landing, as with the SpaceX Falcon 9. And as for the balance between TVC and grid fin actuation, the grid fins would be less effective after a short amount of burn time from the motor. So after like a couple seconds into the burn, the TVC will be primary means of control of the rocket attitude.
Okay, thank you very much. There is a question from Marcus on the chat. How would you envision the sample return system working with your TVC descent architecture?
So we would be envisioning a larger payload. The geometry of the descent vehicle may not be in the form of a rocket for sample return. It can be changed to have a better profile for the atmospheric entry region, because that is a very major concern in sample return. But after the descent region, after the re-entry region, I can see this system being used to pinpoint much more accurately where the sample will land, and can hasten the process of recovery of the sample.
Okay, thank you, Daniel. And that brings us to our last talk for this session, that will be done by Dr. Geoffrey Landis. So Dr. Landis is a researcher at NASA John Glenn Research Center, where he works on developing advanced technologies for space. He has been involved in a number of space missions, including Mars Pathfinder mission, the Mars Exploration Rovers, and the Parker Solar Orbiter. He's a AIAA Associate Fellow and a Fellow of the NASA Innovative Advanced Concepts. He holds degrees in physics and electrical engineering from MIT, and has a PhD in physics from Brown. So please, when you're ready.
Okay. Good afternoon or good morning to those of you on the West Coast. I'm going to talk about a sample return mission from Titan. Is that possible? Let's see, is this not? Sorry, it's not. Why isn't this moving?
Or if you want the slide to move, just ask for the next slide to the.
Okay. So you can't. I can't control it from this side. Okay.
No, you can't control it.
Yeah. Okay. Just a quick look at Saturn and Titan. The fascinating thing about Titan actually is the color. That orange color. Next slide, please. Titan is the only moon in the solar system that, in fact, has an atmosphere, or more than a negligible atmosphere. And interestingly, it's one of the only bodies in the solar system to have liquid on the surface. So here's a view of Titan where you can see both that thick atmosphere, denser than the Earth's atmosphere, and also that orange color. Next slide, please. Here's a view of Titan from the surface. That orange color is organic compounds that are known as tholins. These are the complicated organics that are made from the photolysis and the radiation-induced changes of simple hydrocarbons, incorporating hydrocarbons, oxygen, nitrogen, sulfur, and a vast number of different materials. They're ubiquitous in the outer solar system. You see them all over the place, from Titan all the way to Pluto and Charon and beyond. These are presumably the original building blocks from which life was formed. So it would be a very high science value to get some samples of these, to take them to Earth and analyze them in terrestrial labs. But to date, sample return from something so distant has been assumed to be impossible. So the goal of this proposal is to show that it's credible with reasonable space technology, and that's by using the in situ resources of Titan to produce the propellant for the return to Earth. Next slide. So Titan, as I said, is the other world in our solar system with liquid on the surface, but that liquid is not water. The liquid on the surface of Titan is hydrocarbons, primarily methane and ethane lakes. And that's a lot of methane and ethane lakes. It has far more hydrocarbons than the entire hydrocarbon reserve of the planet Earth. 500,000 square kilometers of lakes. Next slide. So the obvious choice for in situ propellants is to use that methane and ethane. It's the obvious fuel. But chemical propellant, of course, requires both a fuel and an oxidizer. So once you have the fuel, the native hydrocarbon, you have to pick an oxidizer. Our baseline choice is to refine oxygen from Titan's water ice rocks. Titan has an average temperature that is so low, it's in the outer solar system, that actually water is another form of rock. The rocks on Titan are presumed to be primarily water ice. In fact, the methane-oxygen engines optimize at a high oxygen-to-fuel ratio, typically about 3:1. So we end up needing 3 times as much oxygen as methane. So to generate it, we'd gather the water ice rocks, melt them from a radioisotope source, and then electrolyze the water to produce oxygen. Next slide. Methane-oxygen rockets actually turn out to be a fine rocket propellant. They're actually very nearly ideal. The specific impulse is second only to liquid hydrogen, but it has a much higher density than liquid hydrogen. The high boiling point of methane, 111 K, eliminates the need for cryogenic storage. In fact, as I'll talk a little bit later, we can store it at ambient temperature at Titan. Alternatively, we're looking into using the liquid ethane instead. It has a slightly higher density, a little bit lower ISP, and it's also possible that we could use the hydrogen that we produce from electrolyzing the water. Next slide. here's just an image showing that methane oxygen engines are real. The one on the top was the engine for the Morpheus. There it is being tested at Plum Brook Center. In fact, 2 of these engines would be about right for launching from the surface of Titan. I like the image on the bottom. It just shows that kind of beautiful blue flame of the methane. Okay, next slide. Well, going through the delta V and the mass ratios, the total delta V for launching into trans-Earth injection from the surface of Titan ends up being about 7.9 kilometers per second. Interestingly, that's actually the velocity of a minimum Earth orbit, if you were in Earth orbit skimming the surface. So more or less the problem that we're dealing with is nearly as hard as launching from the surface of Earth to low Earth orbit. So our baseline is a 3-stage vehicle. First stage getting us into Titan orbit, then leaving Titan orbit, then doing the trans-Earth injection. The total bottom line is that to get that 7.9 kilometers per second, we're actually ending up with a total of 3.6 tons of propellant. Next slide. We had a student intern draw us a visualization. So here's the student visualization of our launch vehicle launching from the surface of Titan. Next slide. So while the vehicle's mass is 4.5 tons, only about 1,000 kilograms of that needs to be landed. We acquire 3.5 tons of propellants from Titan. That ends up being 875 kilograms of methane and 2,625 kilograms of oxygen. And that ends up being a little bit over 2 cubic meters of oxygen and just about 2 cubic meters of liquid methane. Next slide. So propellant production is tricky. The methane production is relatively easy because there are open bodies of methane on the surface. But the rate limiting step is likely to be the electrolysis of water to produce the oxygen. We're assuming in our baseline calculation to use the Advanced Stirling Radioisotope Generator, ASRG. Nice thing about it is the efficiency is increased because the ambient temperature is very low, and we can use the waste heat from the ASRG to melt the water. Next slide. So calculating the energy, first we have to melt the ice. That requires heating it from the ambient temperature of 90 K up to 273, where it will melt. Then we have to actually produce the power to melt the water. The total for that is 1,800 megajoules, about 500 kilowatt hours. We're assuming this can be done with the waste heat from the electrical power system. The energy to electrolyze the water for the theoretical energy of 18 kilograms per gram of oxygen produced requires 47 gigajoules. This is theoretical. In the real world, it'll be a little bit higher. If we assume 2 150-watt ASRGs, this would take 5 years. It's not entirely impossible, but it's a little bit of a long time. If we can use a next-generation power system, it would take 1.5 years. But we're also looking at an alternative using a nuclear reactor power system based on the NASA kilopower reactor. Next slide. Here's a view of an earlier design study we did looking at a design for a nuclear reactor to be taken to the Titan surface. This is the NASA kilopower design. The total mass for this is about 550 kilograms, but this would now produce many kilowatts of power rather than merely hundreds of watts. Next slide. We have to store the propellants on Titan. Titan has an average temperature of 90.6. It never gets higher than about 93. and is atmospheric pressure a little bit higher than Earth atmospheric pressure. So cryogenic storage turns out to be simple for both the methane and the oxygen. The surface temperature is below the methane boiling point, so we can store the methane as a liquid fuel with no refrigeration. The temperature is above the boiling point of oxygen, but because of the high pressure, we only need to maintain about 1 bar above ambient pressure in the tank, and that will allow the oxygen to remain liquid up to 100 K, which is a comfortable margin above the highest temperature. So by a actually quite fortunate coincidence, the temperature and the pressure at the surface of Titan is just ideally suited for these propellants. The propellant tanks will be relatively high. Next slide. So we are looking into the possibility of actually using inflatable tanks. These would have a smaller volume for the entry vehicle, possibly a lower mass option, and we're looking at this with the trade study. Next slide. So in conclusion, a sample return mission from Titan would be just invaluable for astrobiological science and for understanding the origins of organic compounds in the solar system. The top level analysis of the production and use of in situ propellants shows that such a mission should be feasible. The concept has now been selected by the NIAC program, NASA Innovative Advanced Concepts, and we have just begun a detailed phase 1 study to fill in some of the details. Thank you.
Okay, thank you very much for this interesting talks. We have a question from the chat from Raj Venkatsapathy. The simple return capsule will likely be entering at more than 12 km per second at Earth. Do you know what the entry velocity would be? Is it more like a 15, 16, or what would be the value for that?
Yeah, we haven't yet been looking at the entry capsule, but yes, it comes in at high velocity unless we do some pretty difficult velocity reduction maneuvers. So it'll be a high velocity. I don't have the velocity offhand. I'd have to look up at the trajectory calculations. Sorry.
Okay, thanks. And another question from Hayden Morgan. Is sample collection of fuel oxidizer expected to be autonomous, or at least partially autonomous?
I expect that we will operate it in a way somewhat similar to Mars rover operations, which is the operation itself will be autonomous, which it has to be because of the long light speed delay. But we will have the engineers on the ground upload basically the program. So we'll use human beings to analyze the environment and then upload the program, and then the program will run autonomously.
Okay, thank you very much. Yeah, we're running out of time, so there's another question in the chat, so maybe you could respond directly on the chat if you wish. But otherwise, thank you very much to all the speakers, and especially team for helping us with the slide control. That's it for this talk, and I'll hand over to the POC chair for any concluding comments.
And I'll be quick as well. I wanted to thank every one of you for coming to this session. I think when I last looked, we had almost 160 people at the highest count during the session. So I really appreciate it, especially those of you from the Asia Pacific region where it's dead of night when you were calling in. Our next session is a Mars exploration session. That's going to be on the 8th of July. It will start a little bit earlier. You can see the different time zone times for that. And we also have 4 other sessions after that. You do have to register separately for each one of those sessions. It's just so that you can get the WebEx links separately. So please go ahead and register. Your registration for sample return does not carry over to the Mars exploration session and beyond. And we will try to upload all the presentations onto the IPPW archive and have it open to public as soon as possible. although the posters are already up and ready, and the posters for Mars exploration will also be up within a week before the session. That's it from me, and thank you again for joining us. Have a good rest of the day.